The shift from simple, single-turn AI prompts to complex, multi-turn applications is arguably the single biggest engineering bottleneck in generative AI right now. I mean, when you move beyond a basic script and suddenly need to remember conversation history, route intermediate tool results, track user preferences, and actually wait for human approvals, things get complicated really fast. So let's dive straight into this explainer and unpack exactly why scaling these AI workflows is so inherently painful and how we can actually bring rigorous software engineering back to the table.
You know, it all starts with this deceptive simplicity. A lot of early agentic frameworks let you rapidly prototype a conversational agent using a really basic prompt-in, answer-out loop. And hey, it works beautifully for a proof of concept. But why do these applications just completely fall apart in production? Well, it's because the real world isn't stateless. When you're relying on a hidden loop, where the control flow is totally obfuscated inside some abstraction, things like debugging, system predictability, and enterprise compliance become nearly impossible.
And here is exactly how that evolution turns into a total nightmare. You start with a simple API call. Easy, right? Then you realize you need memory, so you bolt on chat history. Then, oh, the LLM needs to fetch data, so you add tool routing. Before you know it, you are trying to manage real-time streaming, database persistence, tracing, and evaluation data all inside one giant, unmaintainable knot of Python while loops. Welcome to Spaghetti Code 2.0. It's a tangled mess that just destroys your reliability.
This is exactly where we need a major paradigm shift. Enter Apache Burr, which is currently an incubating project at the Apache Software Foundation. Burr is a pure Python, dependency-free, in-process framework. But instead of abstracting all that complexity away from you, it forces you to represent your decision-making applications as explicit, action-driven state machines. It acts as the central control layer designed specifically to manage state and control flow in these complex AI workflows. Now, to truly understand Burr, we really need to establish clear boundaries about what it is not. It is not an LLM provider. It's not a machine learning modeling library. And it is definitely not an inherently rigid AI framework trying to replace your favorite tools. Actually, it is entirely framework agnostic. It's simply the orchestration, persistence, and observability layer that wraps around arbitrary Python code completely without the vendor lock-in or the usual AI hype.
Think about the architectural contrast here. A hidden black box loop buried inside a massive function is a huge liability. When it fails, you literally have no idea why. Contrast that with Burr's approach, which is a highly visible graph of explicitly named actions and transitions. This explicit structure means you can pause, resume, inspect the state, and reason about exactly what happened at any specific node in your application.
So, let's break down the core components of this graph, starting with the action. An action in Burr is really just a Python function that acts as a node in your state machine, but it comes with a very strict programmatic contract. Every single action must declare precisely which pieces of state it reads from and which pieces of state it writes to. There are absolutely no hidden side effects, period. In practice, by dropping in an add-action decorator, you explicitly state, for example, that this specific node reads the chat history and writes the response. That alone makes the entire graph instantly easier to inspect, because before the application even runs, the framework can statically analyze your graph to ensure you aren't, say, trying to read a variable that hasn't been initialized yet. That virtually eliminates a whole class of frustrating runtime errors.
Moving on to the next foundational piece, the state. In Burr, the application state is treated as a strictly immutable dictionary. It is never mutated in place. Instead, a brand new state object is created and checkpointed exactly after every single action completes. Because the state is preserved step by step like this, it unlocks flawless rewinding, replaying, and temporal debugging. You can literally look at the exact state of the system right before an LLM hallucinated.
And integrating this into your Python code is super straightforward. At the end of your action, you just return the updated state. You use methods like .update to overwrite data or .append to safely add to lists, like a chat history, without actually modifying the original array. You are always returning a brand new, perfectly clean state object back to the framework safely and predictably.
Okay, so once you have actions reading and writing state, you obviously need to connect them. That brings us to transitions. A transition is the conditional directed edge of your graph. It determines the routing logic to the next action based entirely on the exact current values residing in your state object. This is exactly how you build out your loops, your fallback mechanisms, and your conditional branches.
You string all these functional nodes together using the application builder and its .with transitions method.
You define, for instance, that after the human input node completes, the system routes straight to the AI response node. By explicitly declaring these edges, you turn functional nodes into a fully visible flowchart. You completely remove hidden control flow and effectively prevent execution deadlocks.
Because Burr is completely agnostic to whatever Python code you decide to run, it supports a massive variety of real-world workflows. It's actively being used right now for complex multi-agent chatbots, huge Monte Carlo data simulations, stateful retrieval-augmented generation pipelines, and highly regulated human-in-the-loop drafting applications where compliance is simply non-negotiable.
And speaking of compliance, let's talk about human-in-the-loop. A standard autonomous pipeline that just runs straight to completion is incredibly risky in high-stakes enterprise environments. But Burr has this amazing capability to halt indefinitely for human feedback. You can literally pause the state machine, save the entire context to a database, and wait days for a human operator to approve an email draft before you resume the workflow.
Executing this brilliant capability is as simple as passing one parameter. When you call your application to run, you just pass halt before and specify the action node. The framework executes right up to that exact boundary, persists the state to your backend, and gracefully yields operational control back to your web server. No locked threads, no nasty timeouts, just robust, resumable workflows.
To bring this all together, Burr treats telemetry as a first-class citizen. It features a built-in tracking user interface that's structured around a really clean, hierarchical data model. You have projects, which represent your code bases. Beneath that, you have applications, which are your individual execution traces, and inside those are steps, the actual actions executed, complete with immutable snapshots of the state before and after. It provides absolutely unparalleled debugging capabilities, and you don't even need to buy into an expensive external SaaS platform.
So we are mapping out a massive 24-segment explainer series on Apache Burr. The 4 major pillars we will be deeply exploring are core model and setup, execution and transitions, persistence and telemetry, and ecosystem and production.
Section 1. Core model and setup, exploring actions and state. Section 2. Execution and transitions, handling conditional routing. Section 3. Persistence and telemetry, utilizing built-in persisters.
And Section 4. Ecosystem and production, mastering advanced features.
As we wrap up this first segment, I really want to leave you with a provocative thought. Take a hard look at your current AI pipelines. How much control do you really have over your AI agents right now? If a critical failure happens tomorrow, can you rewind to the exact state and trace the logic? System determinism is the absolute foundation of enterprise resilience. It's time to take that control back.
Okay, let's dive straight into this explainer and uncover the exact identity and history of Apache Burr. When we're building complex, stateful Python applications and AI agents, truly understanding the foundation and maturity of your tools is absolutely critical for production success. So we're going to strip away the vendor hype today and look at exactly what Apache Burr is and where it actually came from.
Let's kick things off with a rather amusing historical question. Why exactly is it named Apache Burr? Well, the framework actually originated outside the Apache Software Foundation at a company called DagWorks. The creators there had already built a widely adopted data pipeline framework called Apache Hamilton. But when they needed a brand new, highly specific framework to manage complex stateful AI workflows, they named it Burr. If you know your American history, Aaron Burr was the famous rival and eventual killer of Alexander Hamilton. But honestly, this is way more than just a clever naming joke. It points directly to a fundamental architectural difference between the two frameworks.
Now, what's really fascinating here is the architectural duality. Think of it like this. You've got Apache Hamilton built as a straight, acyclic pipeline. It's fantastic for deterministic data transformations, but mathematically speaking, a directed acyclic graph strictly forbids loops. Then, forming the other half of this duality, you have Apache Burr. Burr was designed precisely because modern AI agents fundamentally require cyclic loops. It's like a reason and act loop where an agent thinks, uses a tool, evaluates the result, and loops right back around. Burr acts as that cyclic, loop-capable state machine harness wrapping tightly around those complex decision workflows.
And man, the timeline on this project moved lightning fast. We're talking from an internal tool to a governed open-source standard in almost no time. The very earliest package popped up on PyPy in February 2024, with DagWorks publishing their formal launch narrative the following month, in March. Throughout 2024, the feature set rapidly expanded to include things like state rewind, streaming, and parallel workflows. Fast forward to April 2025, and a formal discussion kicks off to bring the project into the Apache incubator. That all leads to a pivotal date, May 24, 2025, which is when Apache Burr officially entered incubation.
Which brings us to a crucial term, ASF incubating podling. What does that actually mean for us as developers? Well, it's essentially a balanced maturity qualifier. It tells us that the project is highly active, it has strict oversight, and it's currently being released under the rigorous processes of the Apache Software Foundation. However, it's not yet a fully graduated top-level Apache project. It's a clear signal that while the project has robust intellectual property hygiene and community development, you should absolutely still expect the APIs to evolve as it works its way toward complete stability.
Now, because of this transition into the incubator, there's a critical package name shift that you absolutely need to catch for your codebase. Older pre-incubator installations just use the package name Burr, and the release notes are very explicit that those pre-incubator releases are not official Apache releases. So for any new installations today, your requirement files and pip installs must use the official package name, which is Apache-Burr. This is the only way to ensure you're pulling the actively maintained Apache-governed code.
And along with that new name comes formal Apache release discipline. It's a bit of a shift in mindset. You see, the voted Apache source release is actually the authoritative project release. Now, while you and your team will likely still use PyPI wheels and source distributions for everyday installations, those are technically considered convenience distribution channels. We're going to cover exactly how to handle project keys, signatures, and checksums in a later segment, but just know for now that this strict release hygiene is a massive benefit of Apache governance.
So let's weigh this out objectively on a balanced governance scale. Adopting an incubating project comes with some tremendous positives. You're fully protected by the permissive Apache License 2.0, and you get immediate access to a transparent public repository and official mailing lists. But we have to face production reality too. It does carry an incubating status and a beta classifier, meaning some internal APIs are evolving, especially roadmap items around state optimization and exception handling. The developer action required here is non-negotiable. You must strictly pin your versions, diligently read the release notes during upgrades, and thoroughly validate your production assumptions.
All right, moving on to Section 1, from first principles to code, translating the architecture. Let's actually take these abstract concepts and anchor them in some concrete Python code. It starts right here with the @action decorator. In Burr, state is intentionally immutable. Every single update produces a completely new state rather than mutating variables in place. Notice how the decorator explicitly defines reads and writes. You have to declare exactly what state keys this action relies on and exactly what it's allowed to change. This explicit declaration is a game changer. It prevents hidden control flows, stops implicit agent magic, and dramatically reduces those absolutely dreaded key errors in complex LLM pipelines, all because the framework can statically validate your logic before it even runs.
And here's where it all comes together. This snippet brilliantly illustrates how we wire those individual actions up using the application builder. You can see how we chain .with actions to register our nodes, and then use .with transitions to define the exact routing logic. Transitions act as the strict conditional edges routing the logic between our actions. You are explicitly telling the framework, hey, when this condition is met, move from action A to action B. It effectively forces you to map out your application as an explicit flowchart, which is incredibly vital for debugging and human-in-the-loop interventions.
But the builder pattern doesn't just stop at pure logic, which is the really cool part. Notice how .with_tracker local and .with_state persister.supple are changed directly into the application builder. This really highlights the incredible modularity of the framework. You can instantly inject a local UI telemetry tracker to visually monitor your state machine and attach a SQLite, PostgreSQL, or Redis database persister to save and resume your application state. You get all this powerful observability and resumability without altering a single line of your core action logic.
So the philosophy of Apache Burr is pretty clear, right? Favor explicit control, deep observability, and pluggable persistence over high abstraction and framework lock-in. But with this conceptual architecture mapped out, and knowing that we are dealing with an actively evolving Apache incubating project, it leaves us with a rather massive, practical question. How exactly do we securely verify, install, and pin these evolving artifacts to guarantee a rock-solid, reproducible production environment?
All right, let's dive into this explainer. If you've ever banged your head against the keyboard trying to wrangle a complex AI agent, well,
Understanding these 4 building blocks is going to completely change how you architect your systems. We're talking about a real shift here, moving away from those fragile, duct-taped AI scripts and towards explicit, stateful applications.
So how do we actually tame the chaos of an autonomous AI agent? Because as you know, when AI workflows scale up from just simple single-turn prompts to these massive multi-step autonomous systems, tracking exactly how and why they make decisions becomes a huge architectural nightmare. Usually start with a few API calls, right? And then suddenly, boom, you've got this black box of unpredictable loops and impossible to reproduce bugs.
We tackle this by getting on the exact same page with a shared vocabulary, starting with state. Now, in Burr, state is an immutable dictionary, and it gets checkpointed after every single action. It's not just some variable you overwrite willy-nilly. It's a precise historical record of exactly what your application knows at any given millisecond.
Okay, next up is the action. You can think of this as just an ordinary, named Python step that acts as a functional node. But here's the kicker. It adheres to a strict mathematical contract. It explicitly declares exactly what data it's allowed to read from the state and exactly what new data it's going to write back.
Third, we have the transition. This is basically your routing logic. It decides the very next action based purely on the current state. It forms the explicit path your application takes, which completely removes any of that stressful ambiguity about where the execution is actually heading next.
And finally, bringing it all together, we have the application. This is the runnable execution container compiled by the application builder. It takes all those distinct pieces we just talked about, your initial state, your actions, your transitions, plus any identifiers, trackers, or persisters, and bundles them into a highly observable runnable graph.
So let's actually see these core concepts in motion. Picture a super simple flow, a basic loop that shifts predictably from user input to an AI response and then straight back again. It's the foundational heartbeat of a conversational agent, but here it's made entirely predictable.
Now, the really crucial part is how you actually build this in code. Developers enforce this cycle using the @action decorator in standard Python to explicitly declare their data dependencies. By stating exactly what this function reads, say, the chat history, and exactly what it writes, like the response, Burr can statically validate the entire graph before it even runs. Seriously, no more runtime key errors just because an LLM hallucinated and forgot a variable.
But of course, things rarely stay that simple. When workflows scale up, this simple loop evolves into a much more realistic branching graph. Imagine a user input flowing into a route query action, which then dynamically directs the flow to either answering the prompt, executing a specific tool, or summarizing the data. This is what a true autonomous decision-making tree looks like.
And this right here brilliantly illustrates Burr's whole anti-magic philosophy. Instead of burying this crucial routing logic deep inside nested Python if statements, or even worse, handing control over to some black box framework magic, you make these transition paths mathematically explicit. The entire flow of your agent is completely transparent.
When you're using the application builder, you define these transitions with explicit conditions, things like when, expr, or default. By telling the app to, say, move from a query to a tool only when a useTool condition evaluates to true, you ensure there is absolutely zero hidden control flow messing with your agent's reasoning. And because these actions are literally just standard Python, they are incredibly versatile and totally framework agnostic. I mean, they can call an OpenAI client, query a SQL database, or even execute a LangChain pipeline, a Haystack search, or an Amazon Bedrock model. Heck, you can even run pure non-AI logic, like Pydantic validation or Hamilton functions. It's totally up to you.
To put it simply, the real power of Burr doesn't actually come from whatever external vendor tool you happen to be calling. It comes from how transparently you record that tool's impact on the immutable state and how you transition to the next step. Burr doesn't care how you generate your data. It only cares that you strictly declare how that data updates the application. Now, because every single state change is treated as an explicit event, Burr can seamlessly attach built-in trackers and database persisters. This is the exact mechanism that moves you away from those ephemeral, fragile scripts that just vanish into thin air when your server crashes and gets you to enterprise-grade observability where every single step is safely saved to SQLite, PostgreSQL, or Redis. And with that persistence layer in place, you can literally branch off a previous execution using initialized from. You could fork a user session from yesterday,
completely bypassing the need to rerun an expensive LLM pipeline just to test a bug fix on the exact context window that caused the failure in the first place. It is, quite literally, time travel debugging for AI. How cool is that?
All right, let's wrap this up with the 4 essential questions. To really cement this in your day-to-day engineering practice, remember that a compact mental model of a Burr application repeatedly answers 4 essential questions. Question 1 focuses entirely on the immutable state. What does the app currently know? This is where you inspect the exact context window and the explicit data your agent possesses at this very millisecond, beautifully isolated from the rest of your backend.
Question 2 zeroes in on the action. What action runs now? This highlights the specific named Python function that's executing in the current step, totally bound by those explicit read and write contracts we discussed earlier.
Moving on to question 3. We track the output. How does the action update state? Here we observe exactly how the action returned a newly modified immutable state object back to the overall application loop, cleanly appending or updating keys without any hidden side effects.
And finally, question 4 looks at the transitions. Which action comes next? The framework analyzes the newly updated state to explicitly route the execution graph along a directed edge to its next logical step. Or, it just halts if the application is finished.
So by replacing all that implicit framework magic with a highly inspectable state-driven mental model based purely on states, actions, and transitions, the chaos of AI orchestration actually becomes a totally solvable equation. Armed with this level of deterministic control over your models, what will you build next?
We're diving straight into segment 4 of 24, installation, extras, release verification, and development setup. If you've been following our explainer on stateful AI orchestration, you already know that building reliable, observable agents absolutely requires a rock-solid foundation. So today we're looking at the exact commands, the context, and the enterprise hygiene you actually need to install and configure Apache Burr from the ground up. This is all about moving from theory to practice, so we're going to cover everything from a minimal framework install all the way to strict enterprise release verification.
Here's our roadmap for this explainer. We're going to hit core installation and the UI, then modular capabilities, navigating versions, enterprise verification, compatibility cautions, and finally, developer setup and our finale.
All right, part 1. Core installation and the UI.
One of the most brilliant architectural choices the Burr team made was keeping the core foundation incredibly lean. It's basically a fork in the road for how you adopt the framework. On one hand, you've got the minimal core. By just running pip install Apache Burr, you get the orchestration framework and literally nothing else. 0 dependencies at runtime, which is honestly an absolute game changer for production environments where you just want to embed Burr without bloating your app or triggering nasty version conflicts. But for your day-to-day development, you're probably going to want the tutorial and UI path. If you run pip install Apache Burr with the bracket start bracket extra, and by the way, the docs mention the learn extra is exactly the same thing, you instantly get the local tracking server, the CLI, and the whole shebang needed to actually visualize your state machine.
This setup really highlights a clean separation of concerns. Once you've installed the framework with those start extras, all you have to do is type Burr right into your terminal. That spins up the local tracking server. Then, just pop open your browser, head over to localhost port 7241, and boom, there's your dashboard. The framework itself is busy executing your state machine behind the scenes, but it's this optional UI that actually lets you see the telemetry, step through state changes, and check out prompt histories visually.
Moving right along to section 2, modular capabilities.
So because that core package is so incredibly lightweight, everything else you might need is essentially a la carte. Burr relies heavily on optional Python dependency targets, meaning no mandatory baggage, right? So say you want to export standard traces to Datadog. Just install the OpenTelemetry extra. Need to save your agent state between sessions? Go ahead and grab PostgreSQL, Redis, or AI SQLite. Or maybe you want to natively invoke AWS-hosted foundational models. Just snap in Bedrock. It's very much a bring-your-own-stack philosophy. Burr stays completely agnostic to your chosen LLMs, your databases, and your web servers.
Next up, Section 3, Navigating Versions. Okay, this naming transition is absolutely crucial if you're out there piecing together tutorials. If you stumble across older materials from, say, early 2024, you'll see the package just called Burr. Now, those pre-incubator releases are historically useful, sure, but do not confuse them with the official project. Now that Burr is under the Apache Software Foundation's governance, all new projects, literally every new install must use the official package name, which is Apache Burr.
The project has matured super fast. It actually started outside the ESF with a public launch by Dagworks back in March 2024. But zoom ahead to May 2025, and it officially entered the Apache incubator. And as of May 2026, the latest documented snapshot is version 0.42.0-incubating. I want to stress that incubating label. It basically means the project is actively governed by Apache, but is still working through its packaging transition. So yeah, release hygiene matters a whole lot right now.
Which brings us to Section 4, Enterprise Verification.
Look, if you're deploying into a strict, compliance-sensitive environment, a quick PyP install probably isn't going to cut it. The Apache Software Foundation looks at release consumption through 3 distinct lanes. The official, authoritative artifact, that is always the signed source release, which you grab from the Apache distribution page. The PyP packages, the ones you normally pip install, and those pre-built wheel artifacts, Apache officially considers those just conveniences for everyday Python use. Even though they contain the exact same bits, the signed source is treated as the one true source of truth.
So if your org demands strict compliance, here is the exact verification checklist you'll need. First off, download the source release directly from the official Apache distribution page. Next, you've got to import the project's keys file and verify the PGP signature. Usually that's a .asc file. After that, validate the SHA 512 checksum, just to make absolutely sure the file hasn't been tampered with. And finally, you build or install from that verified source, completely following your internal security protocols.
On to Section 5, Compatibility Cautions.
Since Burr is incubating and evolving rapidly, there are a couple of sneaky edge cases you really need to know about to save yourself hours of pulling your hair out. Right now, there's a slight documentation mismatch regarding Python versions. The public downloads page says Python 3.10 or higher is required, but if you look at the pyproject.toml metadata and the contributor setups, they still mention Python 3.9+. Our recommendation? Actually, to be absolutely safe, baseline all your new projects on Python 3.10 or higher. Oh, and if you use Poetry to manage dependencies, trying to install that complex bracketed start target can actually trigger dependency resolution failures.
But hey, don't sweat it, they've documented a workaround. Instead of leaning on that single start bracket, Poetry users should run a specific terminal command that manually spells out the required subtargets. We're talking things like tracking-client, tracking-server, Streamlit, GraphViz, and Hamilton right alongside Logaroo. Doing it this way completely bypasses the resolution issue. Easy fix.
And finally, Section 6, Developer Setup and our finale.
So what if you don't just want to use Burr, but you actually want to get under the hood and contribute back? For the contributor path, you'll first want to fork or clone the repository straight from Apache Gitbox or GitHub. Next up, do an editable install using the developer extra. This pulls in all your testing and build tools. From there, you can run the Python tests using PyTest and build the documentation with Sphinx AutoBuild. Now, quick aside here. If you're tweaking the web UI, that development happens in a totally separate front-end workflow. You literally have to navigate into the telemetry/UI directory and run Node.js commands like npm install and npm start. Keeping this separate is actually super smart because it prevents everyday Python users from getting buried under a mountain of JavaScript dependencies.
All right, once everything is installed, you really should run a tiny smoke test just to verify the framework is humming along correctly. This minimal, deterministic code snippet perfectly illustrates Burr's elegance. By slapping on that @action decorator, we're explicitly declaring that the function reads the key n from the state and writes back to the key n. There is zero magic here. It's just a pure, trackable Python function returning a fresh, updated, immutable state object.
To wrap this whole explainer up into a definitive, reproducible setup card for your team, always create an isolated virtual environment. Install Apache Burr with whatever extras you need, but prioritize pinning the exact version, like 0.42.0. Because remember, incubating projects move fast. Always document whether you're consuming those PyPy convenience artifacts or the verified Apache source releases. Spin up the UI just to make sure your ports are clear, run a minimal state machine example like that counter we just looked at, and record all of this in your project docs.
Having a fully traceable, verified foundation absolutely changes the game for what you can confidently build. You're no longer sitting there guessing what your application is doing in the background. You've got a mathematically rigid, highly observable, and verified state machine running right there locally. The infrastructure is ready to go, so the only question left for us is, what autonomous workflow are you going to orchestrate first?
All right, let's get right into our very first working example, the tiny counter graph.
We're going to build a hands-on Apache Burr application from complete scratch. No magic, absolutely no hidden abstractions, just clean, explicit Python code so we can see exactly how Burr manages state and control flow under the hood.
Here's our quick roadmap. We'll start by stripping away the AI noise, then we'll define our actions and state. After that, we'll wire up the state machine, execute it for our UI reveal, and finally, look at how this scales to advanced workflows.
Step 1. Stripping away that AI noise.
Okay, let's dive into this. When you first start looking at AI orchestration, it is so easy to get completely distracted by things like prompt engineering and API latency. But if we really want to master orchestration, we have to isolate the mechanics. Burr is currently an incubating project over at the Apache Software Foundation, relying on explicit actions and immutable state. And you might notice what's missing there, right? There's zero mention of a specific LLM. It's got this incredibly pragmatic, bring-your-own-model philosophy. It honestly doesn't care if you're using OpenAI, Anthropic, a local model, or, like we're doing today, literally no model at all.
So that brings us to our blank canvas, the tiny counter graph. We're building a purely deterministic Python loop here. Why? Because we want to understand the exact underlying mechanics of stateful orchestration from first principles. We are mastering the absolute atomic units of state today so that when you go off and build these massive multi-agent systems tomorrow, you know exactly what the engine is doing underneath.
Moving right along to step 2, defining our actions and state.
To kick things off, we just need a few essential imports: application builder, state, default, express, and action. That is literally it. We are looking at a modern Python framework that's actually dependency-free at runtime, which, let's be honest, is a rare and beautiful thing. These 5 little imports give us everything we need to build out our entire state machine.
Now, before we even touch the logic, we have to declare our contracts. And this brilliantly illustrates how Burr fundamentally works. Every single action in Burr enforces a strict read and write contract. Our increment action declares it's going to read the count from our state and write a new count. Our finish action? It declares it'll read the count and write a message. If an action tries to read or write a variable it hasn't explicitly declared, the framework is going to catch it immediately. No hidden side effects whatsoever.
So here is how that contract actually translates into Python. We use the add action decorator to bind our reads and writes. Inside our increment function, we safely read the state's count, add 1 to it, and here is the absolute most critical part. We return state.update. We are not mutating the state in place. Burr demands immutable state. Every single update produces a brand new clean state object. And trust me, that's going to make debugging and time traveling through your application's history so much easier later on.
All right, step 3, wiring the state machine. Now we move to the assembly line, putting our graph together sequentially using the application builder. First, we register our actions, increment and finish. Second, we define the transitions, basically how we move from one action to the next. Third, we initialize our state, just setting count to 0. Fourth, we tell Burr our entry point is the increment action. And fifth, we can optionally attach a local tracker so we can visualize everything when it runs. It really just flows like plain English.
Now, what's really interesting about this transition logic is that we're explicitly telling Burr to loop the increment action back onto itself conditionally. We use that xBurr function to evaluate a simple string condition. As long as count is less than 3, keep looping. The second that becomes false, we hit our fallback edge, the default condition, and transition straight to the finish action. Absolutely no hidden control flow going on here.
Step 4, execution and the UI reveal. Time to actually run this thing.
This single line is what kicks off the entire execution. We call app.run, and pay special attention to that halt_after parameter. We are dictating precisely where this execution stops. We're telling Burr, run the state machine, follow the transitions, and halt completely right after you execute the finish action. It then returns the final action executed, the result, and our final state object.
Let's trace that out loop by loop. At 0 milliseconds, the app starts with our initial state of count equals 0. It hits the increment action. Loop 1 updates the count to 1. The transition checks. Is 1 less than 3? Yep. So it loops again. Count becomes 2, loops again, count becomes 3. Now that condition, count less than 3, evaluates to false. The state machine falls right through to the default transition, routes over to the finish action, writes out the final message, and halts. Completely deterministic. And because we attached that local tracker in our builder, we can just pop open our browser to localhost 7241 and see the Burr UI in all its glory. It reveals everything. You get a static visual map of the entire directed graph. You get step-by-step logs of every single loop of that increment action. And you get perfect state introspection, showing exactly how the variables morphed from 0 up to 3. This level of transparency makes debugging an absolute breeze.
Finally, step 5, scaling to advanced workflows.
Okay, yes, we've just built a tiny toy counter today. So the crucial point is this. The fundamental mechanics remain completely identical as you scale. The tiny counter graph uses immutable state, conditional transitions, and tracked actions. When you go out and build enterprise agent workflows, pulling in an LLM, doing complex routing, hooking up PostgreSQL, or streaming checkpoints, you are literally using the exact same application builder, the exact same transitions, and the exact same decorators. Which leaves us with this final thought. If an orchestration framework can flawlessly, deterministically track and manage a simple little counter loop from pure first principles, giving you total observability at every single step, what can these exact same deterministic mechanics do when applied to your most unpredictable, complex, multi-agent chatbots? Let's jump right into this explainer and meticulously break down Burr's action nodes. If you've spent any time building stateful AI applications, you already know exactly how fast control flow can turn into a tangled mess of hidden variables and completely unpredictable LLM outputs. Well, today, we're going to fix that. We're starting from the absolute simplest Python decorators and working our way up to advanced, class-based objects, so you can see exactly how Burr orchestrates these core compute units.
We're taking a bottom-up approach to the architecture today. We'll quickly move through the action node anatomy, the read-write contract, runtime inputs versus state, injecting application context, action return mechanics, and finally, graduating to class actions.
Starting off with Section 1, the action node anatomy, which is really the core compute unit of Burr. So the main thing to grasp here is that an action in Burr is essentially a named unit of work. It acts as a highly discrete, mathematical node inside your state machine graph. It's not a mysterious black box. It's a very explicit step in your application's reasoning process.
Literally every single action you write in this framework is going to follow a strict, highly predictable 4-step lifecycle. First, it reads exactly the state it declared it needs, nothing more. Second, it accepts any ephemeral runtime inputs from the user or the system. Third, it computes something, like calling out to an LLM or hitting a database. And fourth, it returns a freshly updated state. This design is what completely eliminates those hidden control flows that keep you up debugging at 3 a.m. and ensures your AI application is completely observable from the outside in.
To put that into perspective, take a look at the absolute simplest form of this API. It's just so clean. What we have is a standard Python function that explicitly accepts an immutable state object and returns a newly updated state. Just by dropping that @action decorator on top, we've instantly transformed a basic Python increment function into a fully trackable node within our state machine graph. Moving right along to Section 2, the read/write contract and how we establish strict boundaries. What's absolutely fascinating about this next concept is how Burr enforces a strict visual contract on every single node using those read and write declarations we just looked at. It's not just polite documentation, it's basically the law of your application. By explicitly declaring what goes in and what comes out, you're obviously documenting developer intent. But here is the real kicker. The framework can actually use that to mathematically validate your execution graph. It looks at your entire pipeline and stops catastrophic errors, like getting a key error from some undeclared variable way before they ever hit production. Basically, if an action doesn't explicitly declare that it writes to a variable, it literally cannot accidentally overwrite it. That brings us to Section 3, runtime inputs versus state, distinguishing between ephemeral variables and durable memory. We really need to understand how your action interacts with external variables, because blurring the lines between runtime inputs and workflow state is a massive source of bugs in AI agents. Take a look at the parameters in this chatbot snippet. The prompt parameter is a runtime input. It's injected at the exact moment of execution, when a user types a message. On the other hand, the chat history is pulled directly from the overarching durable state. The function just blends the two together seamlessly.
This juxtaposition is totally critical to wrap your head around. Runtime inputs are strictly for the current execution cycle. They're highly ephemeral. We're talking about raw user text, live API clients, or temporary database handles. You obviously wouldn't want to save a live API client to a database, right? But your state? That contains the durable business facts, like your conversation history, that the workflow absolutely has to remember for tomorrow. It's the stuff that survives tracking, database persistence, and historical replay.
Next up is Section 4, Injecting Application Context and Getting Awareness of the Runtime Environment. Because as your nodes get smarter, they inevitably need to know a bit about their surrounding environment to do their jobs effectively.
Burr handles this with a special parameter, literally called _context. It acts as your gateway to the orchestration layer. By just adding this parameter to your action, you automatically pull in crucial runtime metadata. We're talking about the current application ID, the partition key tying a run to a specific user, or the exact sequence ID of the step. For robust enterprise tracing, this is absolutely required.
Passing this context into your function is a total game changer for audit records. You can instantly tag external logs in Datadog or OpenTelemetry with the exact app ID. But quick word of caution here. You have to make sure this context object never replaces your explicit state for the actual facts your workflow relies on to make decisions. The rule of thumb, keep metadata for monitoring and keep state for application logic.
All right, let's hit Section 5, Action Return Mechanics, specifically how we separate results from state mutations. How an action actually hands data back to the framework is a big deal for proper debugging and building clean APIs.
See, sometimes what your AI computes isn't exactly what it needs to commit to memory. Function actions in Burr let you neatly separate the intermediate, observable result, which is what the caller or the UI actually sees, from the durable state mutation, which is what the application remembers next. Doing this ensures that request scope data doesn't accidentally get saved to your database and bloat your storage.
Check out how brilliant this separation is in a streaming context. By returning or yielding a tuple, the first item, the result chunk, flows instantly straight to the user's screen. Meanwhile, the second item, the final state update, is meticulously tracked and persisted to the database behind the scenes, but only when the generation is completely finished. It's just a perfectly clean separation of concerns.
So that begs the question, when exactly should your architecture graduate from these simple function actions over to more robust class actions? As your AI agent's logic gets increasingly sophisticated, you're going to hit the limits of simple Python decorators. You'll end up juggling complex API clients, heavy initialization logic, or deep class hierarchies.
And that leads us right into Section 6, graduating to class actions for object-oriented state transitions. This API is purpose-built for advanced, highly structured enterprise use cases where object-oriented principles aren't just nice to have, they're necessary.
You'll want to step up to class actions when you really need to reuse action objects across completely different application graphs. Like, say you have a highly tuned RAG retrieval node. Wrapping that in a class means you can instantiate it with different parameters across 10 different chatbots. It's also absolutely perfect when you need to carefully separate the messy network execution from the state mutation logic.
Here's exactly how that separation plays out in the code. By explicitly splitting the architecture into a stream run method and an update method, Burr forces a really beautiful design pattern. You isolate all the messy unpredictability of LLM network calls inside the run phase. Then, once you finally have the result, it gets passed into the update phase, which is a rigid, mathematical, synchronous update of your state machine. Meaning, if the network drops, your state is never corrupted.
As we wrap up this deep dive into Burr's action architecture, I want to leave you with a thought to chew on. Take a hard look and ask yourself, is your current AI stack truly this inspectable? Are you explicitly managing your state boundaries, or is your framework hiding critical logic in the shadows? Because trust me, when your multi-agent system goes totally off the rails in production, having explicitly defined, trackable action nodes isn't just a nice-to-have. It's literally the only way you're going to figure out what went wrong.
State is the absolute central character in Apache Burr workflows. It's not just some passive bucket of variables you can toss things into. It operates as a strict, immutable, dictionary-like object. Today, in segment 7 of 24 of our Explainer series, we're focusing specifically on immutable state updates, appends, schemas, and serialization. We're going to break down exactly how this immutable design protects your AI applications from chaotic data mutations.
Here's our roadmap for today. We'll cover the immutable state object,
the state execution timeline, designing stable state keys, typed state and schemas, and finally, serialization and production hygiene.
All right, let's jump right into Section 1, the immutable state object.
To really get Burr, you have to realize that actions don't actually own the data. They're just temporary guests visiting the state. In Burr, state is explicitly defined as an immutable, dictionary-like object that actions use to communicate and transition safely. This architecture inherently rejects the idea of in-place mutations. That's a massive shift if you're used to just modifying a global Python dictionary whenever you feel like it. State is the star of the show here, and it plays by very strict rules.
When you want to change something, you don't overwrite it directly. Instead, you use specific methods provided by the state API. For instance, state.update replaces or adds a key with a new value. State.append safely adds an item to an existing list array. Doing some math, state.increment mathematically adds to a numeric key. And if you need to clean house, state.wipe clears all state keys except the ones you specifically tell it to keep.
And here is the absolute golden rule, folks. Burr state operations do not mutate in place, ever. They return a brand new state object. If you ignore that returned object, say you call an update but don't actually return the result from your action, literally nothing changes. Your state stays exactly the same. It's a deliberate design choice to prevent side effects and make sure every single transition is mathematically pure.
Moving on to Section 2, the state execution timeline.
Let's actually visualize this isolated processing window. Before an action even starts, at t = 0 milliseconds, your current state is a fixed snapshot, like count = 1. During the action, at t = 50 milliseconds, the framework subsets the state, handing the action only what it declared it needs to read. The action computes count + 1. Then, boom, at t = 100 milliseconds, the action yields a completely new state snapshot, count = 2. It's a clean, discrete jump from one immutable snapshot to the next.
So why does this strict timeline matter so much? Well, if you're an enterprise team building complex AI agents, it's a total game changer. Because the state is preserved as an immutable snapshot at every single step, you get flawless local observability. You get exact replayability of prior states. It builds immutable audit trails, super critical when a wildly non-deterministic LLM makes a sensitive decision. You can do temporal debugging without corrupting memory. You can literally pause and see exactly what the LLM saw before it hallucinated. And my favorite, you can safely fork workflows from earlier sequence points. If a tool fails, just rewind, fix the prompt, and resume.
Let's look at Section 3, Designing Stable State Keys. How you name the keys in your dictionary is make or break for your state machine. Good state design means using crystal clear, stable keys. Think chat history, intent, tool result, draft, or final answer. These make it completely obvious what data is flowing through the system. Bad design? That's when you rely on massive, ambiguous catch-all blobs like data or context. If your routing depends on clear fields to make decisions, dumping everything into one giant blob is going to make your transition logic incredibly fragile in production.
Oh, and a quick but super important developer detail here. Private keys that start with double underscores, like __ sequence ID, are reserved internally by Burr. Seriously, do not modify these directly. The framework uses them to maintain execution sequence and manage the persistence layer. If you mess with them, you'll corrupt your internal tracking and database records.
All right, Section 4, type, state, and schemas.
This is where we add some serious discipline. Loose dictionary state is awesome for rapid prototyping or if you're just writing a quick script by yourself. It's fast, it's flexible. But when you move to a multi-developer team, you really need Pydantic-backed typed state. It doesn't replace the state machine model. Rather, it acts as a strict shared contract so everyone knows exactly what keys and value shapes the workflow expects.
Setting this up is basically building a defense layer. First, you attach application-level typing constraints right onto your application builder using the with_typing method. Next, you declare richer input and output expectations for each individual action. Because these schemas validate data on the fly, you'll instantly catch wonky LLM or tool outputs way before they cascade into massive pipeline errors downstream.
And when you're persisting data across different container deployments or web APIs, strict schemas are absolute lifesavers. Remember, persistent state heavily outlives a single process. Honestly, it outlives a single developer's memory. Typing inherently self-documents your workflow. If you're embedding Burr in a FastAPI server, those schemas make your API boundaries crystal clear. It hardens loose strings like intent or citations into validated fields, catching bad JSON before it poisons your persistence layer.
Which brings us to our final part, Section 5, Serialization and Production Hygiene.
Let's talk about the pragmatic reality of actually saving these objects into your database. Standard Python dictionaries? Burr handles those right out of the box for SQL, Postgres, or Redis. But richer objects need explicit SERDE, that's serialization and deserialization. Pydantic models need custom extraction to JSON. Vector embeddings require explicit array compression choices. And binary document payloads, you have to map those to specific backends so you don't accidentally break your database.
You really have to design state values that are durable. Make them easily portable across environments. Ensure they are versionable because, let's face it, your schemas are going to migrate eventually. The golden rule here, default to standard JSON serializable structures whenever you can. Build it so that when your app inevitably evolves, your persistence layer doesn't shatter.
Now, a quick dose of reality straight from the docs. Typed state improves discipline, but richer validation remains an evolving area in Apache Burr. Basically, treat schemas as a production hygiene tool, not some magical bug eradicator. You still absolutely need rigorous tests, careful migrations, and Burr's replay capabilities. Schemas are amazing, but they won't automatically fix every flaw in your logic.
So, I want to leave you with this provocative thought as you design your own architecture. If your application crashes halfway through an agent loop, will your state schema let you resume flawlessly, or is it going to break your database? It's a critical question you absolutely have to answer.
Let's jump right into Segment 8 of our Apache Burr Masterclass. For this explainer, we're focusing entirely on how we actually control the flow of execution from first principles. So if you've been following along, you already know Burr is all about explicit state machines, right? But look, a state machine isn't just a bucket of disconnected actions. It's really about how we securely and predictably move between those actions.
Here's the agenda for today's explainer. 1. Transitions, the graph's edges. 2. Conditional routing in Burr. 3. Evaluation order and fallbacks. 4. Loops, the agentic superpower. And 5. Routing state best practices. Starting off with Section 1, Transitions, the graph's edges.
So, picture this. An action just finished running its Python code and safely updated the immutable state object. Basically, the framework just generated some shiny new data. Maybe it appended a chat message or, grabbed an API response. But that immediately brings up a pretty critical question. How exactly does Burr know what to do next?
Well, the answer lies in transitions. Conceptually, transitions are the directed edges of a Burr graph that connect your action nodes together. They mathematically dictate the exact routing logic to get you from one state to the very next one. You can really just think of them as the literal train tracks your application runs on. In a lot of traditional LLM pipelines out there, control flow gets buried inside messy loops or nested if statements, which makes debugging an absolute nightmare. Burr totally flips that and forces you to make these tracks explicit.
Now, there are two main types of tracks we're dealing with. On one hand, you've got an unconditional transition. That's your straightforward script where, say, a human input action always flows directly to an AI response. No questions asked. But on the other hand, we have conditional transitions. This is where, after a route query action, the graph branches out into multiple potential paths based on a specific state variable, like an intent field. And honestly, this is exactly where your system transforms from a static, boring script into a truly dynamic agent.
Let's move on to Section 2, Conditional Routing in Burr.
Burr makes this branching logic incredibly readable. When you're building an app, you explicitly declare these conditional transitions using Burr's built-in Python helpers. So we're basically telling the graph, hey, from the route query node, route over to answer question when the intent is a question, or go to execute tool when the intent is a command. There is absolutely no hidden magic going on in the background here. The entire topology of your AI application is clearly laid out in plain Python.
To actually pull this off, Burr provides pre-documented condition helpers. First up is xBurr, which lets you do expression-based evaluation. Super handy for mathematical logic, like checking if epochs are greater than 100. Second is when, which gives you a really clean key-value style matching right against your state variables. And finally, there's default, which acts as your ultimate fallback safety net if absolutely no other conditions are met.
All right, into Section 3, Evaluation Order and Fallbacks. Let's break down exactly how this checking sequence happens, because order totally matters here.
transition conditions are evaluated in the strict, exact order you declare them in your code. So, in step 1, if checking whether the intent is a question evaluates to false, it simply moves down to step 2. Then, if checking for a command evaluates to true, execution routes there immediately. The golden rule: the first true condition always wins, and any checks after that are completely ignored.
But that brings us to a major pitfall you've got to watch out for: the missing default trap. Because think about it, if no conditions evaluate to true, and you forgot to add a default transition, your application doesn't just guess what to do next, it halts immediately. It basically leaves your state machine completely frozen in the void. So always include a default route so you can gracefully handle those weird edge cases.
Moving to Section 4, Loops, the agentic superpower.
You've really got to notice the architectural difference between execution models here. Strict Directed Acyclic Graph Execution, or DAGs, like what Apache Hamilton uses, forces execution to flow strictly in a single, one-way direction. It mathematically prohibits cycles. Burr, however, totally embraces cyclic state machines. It explicitly supports cyclic graphs, and this native support for looping back on previous states is honestly Burr's biggest differentiator when you're building autonomous AI system.
Because, let's face it, loops are your agentic superpower. I mean, a standard chatbot, that is essentially an infinite loop, just bouncing from user input to an AI response and back again. A React-style agent loops continuously through observing, reasoning, executing tools, and replanning. Or think about a human review workflow. You loop through drafting, getting human feedback, and revising until you finally get that stamp of approval. Loops make all of that possible.
Finally, let's hit Section 5, Routing State Best Practices.
If you take away literally just one production rule from this explainer today, make it this: routing should be driven by small, explicit state fields, not buried inside raw generated text. Seriously, never rely on parsing massive blocks of unpredictable LLM output just to figure out your routing. That is a guaranteed recipe for a fragile system that will totally break the very second the language model decides to slightly tweak its formatting.
Instead, what you want to do is go inside your action nodes, have your Python code neatly parse that LLM response, and extract small, explicit, highly predictable state fields. We're talking things like an intent string, a status flag, a boolean for needs clarification, or a specific tool name. You write those clean fields into your immutable state and then use those precise fields to drive the when and expert conditions on your transitions. Doing it this way completely decouples your routing logic from the wild unpredictability of AI text generation.
So as you sit down to design your next generative AI system, take a really close look at your architecture. If your AI agent lacks explicit, inspectable cyclic transitions, is it truly a controllable state machine? Or is it just a brittle script full of hidden loops waiting to break the second it hits production? All right, let's dive right into how Apache Burr actually empowers you to assemble, execute, and, most importantly, strictly control your stateful Python applications. Look, if you're building AI agents or complex decision systems, you already know that managing state and execution flow is, well, it's usually where things get super messy, right? It often devolves into this tangled spaghetti code of endless while loops. So in this deep dive, we're going to look at the exact under-the-hood mechanics Burr uses to completely solve this.
Here's our roadmap. 1. The assembly line. 2. Graph and API separation. 3. Execution modes. 4. Halting conditions. 5. Visualization. And finally, 6. Deliberate controllability.
Section 1. The assembly line. Application builder.
To start things off, you need a centralized factory to compile your ordinary Python actions into a runnable state machine. And that's exactly what this builder chain is. Think of it like snapping together interlocking frosted glass modules. You sequentially add your core logic with .with actions, you define your routing rules with .with transitions, and you initialize the starting memory with .with state. And from there, you literally just snap on the rest. You set your entry point, define identifiers, and attach crucial runtime layers like trackers, state persisters, lifecycle hooks, and even parallel executors, all of which, by the way, are backed by really robust typing support. This setup cleanly compiles your explicit actions into an inspectable graph without relying on any hidden framework magic. Honestly, the code reads almost like plain English. You're telling Burr exactly which functions to run, how they flow from, say, human input to an AI response, and what the starting state is. When you hit that .build method, boom, you get a standalone, executable application context that is completely ready to run.
Moving on to Section 2.
graph, and API separation.
Now, as your systems scale up, tying your core logic directly to a specific deployment environment becomes a massive liability. It's a huge pain. Burr actually solves this by entirely decoupling the reusable workflow graph, meaning your actions and transitions, from the application-level runtime concerns, stuff like state, entry points, tracking, persistence, and hooks. By isolating your logic this way, you gain the absolute superpower to deploy the exact same state machine in wildly different contexts.
Check this out. You can instantly see how one reusable graph translates seamlessly across different environments. During local dev, you might just attach a local file system tracker and some basic in-memory state. Easy. Then, for an automated test run, you strip that away, swap in mocked tracking, and use a test ID. But in production, you take that exact same core graph and wrap it with an S3 tracking server, a PostgreSQL persister, and strict tenant partition keys. You literally never have to rewrite your core AI logic just to scale it up to production.
Which brings us to Section 3 execution APIs and iteration.
Okay, once your application is built and instantiated, you need deliberate APIs to actually drive it forward. Picture a glowing cursor moving across your graph nodes. The run command lets that cursor flow continuously until a halting condition is met. But step, that gives you manual node-by-node iteration control. So a standard chatbot is going to use run to process a prompt all the way to a final response. But if you're debugging a really complex multi-agent simulation, man, step is incredibly powerful because it lets you evaluate the immutable state after every single action.
And if you're dealing with high concurrency, like maybe a FastAPI web server handling hundreds of users at once, Burr fully supports asynchronous execution with a run and a step. But a quick word of caution here, the documentation is very strict on this. Your custom actions must be natively async. It has to be async all the way down, meaning you absolutely must use explicit await-based I/O so you don't accidentally block the main thread.
Section 4. Mastering halting conditions.
Look, AI agents are rarely just fire and forget, right? They almost always need to pause for human oversight or to trigger external side effects. So the distinction in how you halt your graph is absolutely vital. You're going to use halt after to seamlessly return an AI's result to a user after a specific action finishes. But you've got to use halt before to pause the system when it's pending external input or a human-in-the-loop approval. The system essentially just idles right before executing that specified node.
Let's look at a concrete example. By explicitly running the app with a halt before target, you guarantee your application safely suspends to a database right before doing something critical, like sending an email. This is brilliant, because it allows your stateless web server to go off and handle other users. The Burr persister automatically checkpoints the exact state right there. Then, hours later, when a manager finally clicks approve, the server just reloads this exact state using the unique app ID and resumes execution flawlessly.
Burr also handles finality with explicit precision. Instead of hiding your termination logic inside some random standard action, the result node keeps the graph's conclusion totally visible and strictly typed. By explicitly routing your workflow into a result action, you mark a clean, definitive outcome. The framework exposes that finalized result directly to the caller, which completely removes any ambiguity about whether the state machine is actually finished or if it's just paused.
All right, Section 5, Inspection and Visualization Tools.
Because Burr intentionally avoids those frustrating black box abstractions, literally everything happening inside your state machine is highly visible. At any given moment, you can pause execution and deeply audit the exact memory state, the action outputs, and the routing decisions. Because state is immutable and it's tracked after every single action, you get a perfect historical record. You can dynamically inspect application.state, review the runtime identifiers, and verify exactly why a specific route was taken. No more guessing.
And it gets better. By simply installing the GraphViz Extra, running this single command generates a sleek, literal blueprint of your architecture. And here's a major pro tip for you. Always use the include conditions equals true parameter. That ensures the generated image doesn't just show you the basic nodes, but it actually maps out the exact routing conditions, like when confidence is greater than 0.9, directly onto the edges of the graph itself.
This visual graph essentially acts as living documentation. It completely ensures that the routing rules you see on screen perfectly match the actual code executing in production. Instead of forcing a new team member to read through hundreds of lines of complex while loops to understand an agent's behavior, they can just look at the generated Burr graph. It's an absolutely invaluable, strictly accurate asset for code reviews, onboarding,
and especially for tracking down production incidents.
Section 6. The Principle of Deliberate Controllability.
Everything we've covered today really points back to Burr's foundational philosophy. Your LLM might be probabilistic, but your orchestration layer absolutely cannot be. Your AI workflow must be entirely under your command. You are never fighting the framework here. You explicitly dictate which graph to instantiate, the start points, the inputs, the persistent backends, and exactly where the machine stops and how it resumes. Total control.
With the execution engine fully exposed and the application chassis ready to be configured to your exact needs, the architectural possibilities are entirely in your hands. You've got all the tools to build highly observable, resumable, and strictly auditable AI applications. So you now wield total deterministic control over your AI state machines. What resilient, enterprise-grade workflow are you going to build next?
We're diving right into a very acute pain point in modern software development today: debugging non-deterministic AI state. Look, if you're building agentic workflows, you already know large language models are completely probabilistic, but the orchestration surrounding them absolutely has to be deterministic. In this explainer, we're going to break down exactly how Apache Burr solves this headache using its powerful tracking UI.
We'll be moving through a quick introduction to bird tracking, breaking down the tracking hierarchy, debugging a chatbot hallucination, looking at UI portability and curation, contrasting tracking versus persistence, and finally, covering operational tracking and security.
So let's kick things off with Section 1, an introduction to Burr tracking. Imagine you're running a multi-agent system, or honestly, even just a complex chatbot. When that system hallucinates or fails, and you're dealing with hidden control flows, it is virtually impossible to reconstruct the exact context the model was looking at right before it crashed. You're just left guessing in the dark. Burr's entire philosophy is to completely eliminate that guessing game by enforcing explicit state machine contracts.
Okay, so how do we actually see what's happening under the hood? Burr's built-in answer is explicit tracking. It's incredibly simple. You just append the with tracker method to your application builder in Python, passing in local and your project name. Then run the Burr command in your terminal, and boom, you instantly get a local dashboard running on port 7241. And the best part, this isn't some third-party SaaS tool. It's a self-hostable UI reading straight from a local file system telemetry buffer. You are literally watching your application think in real time.
Moving right along to Section 2, let's look at the tracking hierarchy.
Burr organizes all this telemetry data really cleanly in a strict hierarchy. First, every tracked run is grouped by project. You can think of this as your top-level codebase. Right under that is the application, which is essentially a single continuous trace or session, and that's bound by an app ID and a partition key, like a specific user's ID. Finally, you drill all the way down into the executed action or step. Each one of these steps is tracked linearly with a strict sequence ID. That means you capture exact state snapshots, inputs, outputs, and timestamps across the entire timeline.
Next up, Section 3, debugging a chatbot hallucination.
This is the million-dollar question, isn't it? When you hit a wrong route or get some bizarre LLM output, you don't want to just guess what happened next. You really need to ask, what happened right before this? To solve this, Burr lets you do what we call the mental rewind. You literally just click backwards through the actions. First, check the stored tool output, like did the API return some malformed JSON? Second, inspect the exact variables. What exactly did the route query action write to the intent state key? Because that tells you precisely which conditional transition fired. And third, you can review the exact chat history state array from the split second before the error. Because Burr records immutable state snapshots at every single sequence ID, the exact state before and after is totally exposed. This is the practical, everyday value of making explicit state and transitions highly visible.
Let's jump into Section 4, UI portability and curation. Now, you don't always want to context switch out of your development environment just to check a dashboard. So you can embed the UI right into your Jupyter or Colab notebook using the IPython magic command %burr UI for super rapid interactive exploration. Or if you're building out a production backend, you can actually mount it directly onto an existing FastAPI service using mount burr UI. This gives your team immediate internal developer visibility right alongside your API endpoints.
But this UI isn't just a passive viewer. Engineers use it as an active curation tool. You can filter runs, inspect weird routes, label specific AI behaviors, and compare good versus bad traces side by side. But here is the absolute game changer. You can export these captured state snapshots. Using the Burr test case create command line tool, you can turn a historical production trace into a deterministic, repeatable regression test in PyTest. You're literally converting observed anomalies into permanent testing evidence, and you don't even have to hit those expensive external AI APIs again to do it.
Section 5. Tracking versus persistence.
Before we talk production, we have to draw a really hard architectural boundary. Tracking is an observability timeline strictly designed for humans and for debugging. It logs the metadata, the graph structure, the timestamps. The persister, on the other hand, uses durable databases like SQLite or PostgreSQL for actual application state. The persister is what allows your system to pause, wait for human feedback, and then resume execution days later. So, while they are intimately connected, they are absolutely not interchangeable. Never rely on your tracking UI buffer to recover your mission-critical application state.
Finally, Section 6, Operational Tracking and Security. When you finally move away from the local file system to something like S3-backed tracking, or if you're pushing metrics to OpenTelemetry, you're now sending highly sensitive data across a network. Think about it. This telemetry data contains exact LLM prompts, raw model outputs, intermediate reasoning steps, and potentially raw user data and PII. This demands incredibly strict security planning and robust retention policies.
And we actually need to explicitly call out a limitation here regarding the project's incubating status. Authentication and access control lists for the S3 tracking server are currently listed in the official roadmap as future work. That means you cannot just expose this tracking server to the public internet. It's a fantastic building block for sure, but production teams are entirely responsible for wrapping it in proper network controls, reverse proxies, secret management, and data redaction. You have to lock down that perimeter yourself.
Ultimately, Apache Burr gives you the deterministic visibility required to build actual, verifiable trust in your AI applications by replacing guesswork with explicit contracts. But it leaves us with a critical question to chew on as you design your next system. Are your agent's intermediate reasoning steps fully secure, completely traceable, and entirely auditable before they ever interact with a customer? Keep that front of mind as you architect your state machines.
Let's dive straight into segment 11 of this explainer: persistence, resume, fork, and durable state. We're going to tackle a fundamental architecture problem today, which is how Apache Burr gives stateless servers the durable memory required for complex AI workflows. Because if you're building AI agents, you already know these systems simply cannot afford to be forgetful.
Here is what we're looking at. First, the need for durable memory, followed by identity and state tracking. Then we'll cover choosing your persistence backend, the sync versus async architecture choice, time travel with resume and fork, and finally, payload discipline and serialization. Part 1. The need for durable memory. To really get why Burr's persistence is such a game changer, we first have to look at the tension between traditional web architecture and modern AI agents.
Think about traditional web servers or serverless functions. They're built to be ephemeral, right? They spin up, handle a request, and instantly forget everything. But AI assistants? Totally different story. They desperately need a continuous memory context that can survive multiple requests, random server crashes, long background pauses, and human-in-the-loop delays. Say your agent is waiting 3 days for a human to approve an email draft. A stateless architecture is going to lose that context entirely. Burr addresses this head-on with state persisters that take snapshots of your execution, allowing you to hydrate that exact state back into memory whenever you need it.
Moving to part 2, identity and state tracking. Because, well, before we can actually save state, we need a bulletproof way to identify and track it.
These 3 identifiers are the secret sauce. They would allow a brand new process to perfectly rebuild a Burr application and initialize it from a stored snapshot. First up, the application ID. This identifies a specific run. Think of it as a single chat thread or a unique email drafting workflow. Next is the partition key. This logically groups those sessions together, usually by user, tenant, or namespace, which is absolutely critical for multi-tenant enterprise setups. And third, the sequence ID. This tracks the exact step execution linearly. Every single transition through your state machine increments this ID, so we always know exactly where the agent is in its journey.
All right, part 3, choosing your persistence backend. The beauty here is that Burr doesn't force a single one-size-fits-all database on you. It uses pluggable persisters to match whatever architecture you're already running.
Deciding between these options really comes down to your architectural trade-offs. SQLite, fantastic for local dev, rapid demos, and simple single-node deployments, but it's definitely not the default answer for high concurrency production services. For that, PostgreSQL is your enterprise standard,
bringing durable storage, strict ACID guarantees, and efficient connection pooling. Then you have Redis, which is perfect for low latency or ephemeral state, where raw speed is everything. Just make sure you configure your eviction and durability settings to match your workflow. And MongoDB is great for document-shaped or deeply nested state. One quick caveat from the documentation, though, asynchronous support isn't always perfectly symmetrical across all these backends. Oh, and if you have specific compliance rules, Burr makes it super easy to roll your own custom persisters.
Part 4 focuses on sync versus async architectures. Now, choosing between synchronous and asynchronous persistence isn't just some magic performance switch you flip. It's a deliberate architectural decision.
If you're running a simple synchronous service, using a sync persister is totally fine. But what if you're running async FastAPI endpoints, streaming services, or hitting high latency database calls? In that case, you have to use async persisters, like the async PostgreSQL persister you see here. If you drop a blocking synchronous database call right into an async web server, you're going to block the entire event loop and absolutely destroy your concurrency. Burr provides distinct sync and async drivers so you can perfectly align your persistence layer with your application's concurrency model.
Part 5. Time travel, resume, and fork. Because Burr explicitly tracks state using those sequence IDs we talked about, we can literally navigate time.
The initializeFrom method is the foundation for this time travel. When a stateless server gets a new request, Burr queries the persistence layer, deserializes the historical state up to a specific point, and fully hydrates the state object. But look at those parameters, fork from app ID and fork from sequence ID. By using those, we aren't just resuming, we're actually instructing Burr to branch off from a precise historical moment.
Think of your execution like checkpoints on a branching road. Let's say a previous run went through sequence IDs 0, 1, 2, and 3. A new application can initialize from sequence 3 to just resume where it left off. But, incredibly, it can also fork all the way back at sequence 1 to explore a completely alternate path. This is massively valuable, whether you're debugging a hallucination, running what-if data science analyses, or doing Monte Carlo simulations where you need to replicate an exact environment before introducing new variables.
Finally, Part 6, Payload Discipline and Serialization. Look, saving state is a superpower, but if you do it carelessly, you will tank your database performance.
This is where strict payload discipline comes in. State tracking and persistence get unbelievably expensive if you just dump every variable into Burr's state dictionary. You absolutely should not store large documents, multi-dimensional vector embeddings, massive binary blobs, or full provider API responses directly in Burr's state. Instead, you want to store compact routing fields, string IDs, URIs, and summarized histories. Keep all those massive payloads externalized in object storage like S3 or dedicated vector databases. You want to choose your action granularity so that each checkpoint is incredibly useful without becoming bloated.
And we have to talk about serialization. If you're storing complex Python objects or strict pydantic models in your state, it's not going to be magically JSON serializable by default. You must explicitly manage custom serialization and deserialization. Burr handles this cleanly through custom persister logic or the surda kwrgs parameter you see here. Doing this properly ensures that malformed LLM outputs get caught immediately during execution, which stops downstream logic errors from corrupting your database.
When it comes to production, live by this rule. Durable state should be boring, portable, and versionable. You want highly stable schemas. Always test your actual state objects against your chosen backend database before deploying, and please never try to store unserializable artifacts like active network sockets or unpickled API clients in your state.
So are your AI workflows truly resilient across distributed environments, or are they just one server crash away from total amnesia? Treat persistence as a core pillar of your architecture, not an afterthought you bolt on right before deployment. By leveraging Burr's explicit state machine and pluggable persisters, you're building AI workflows that won't just survive the chaos of distributed production environments, they'll actually thrive in it.
Segment 12, Building a Simple Chatbot with Burr. So, we spent some time digging into the theory behind state machines and the mechanics of persistence, right? Well, today we are bringing all of that theory directly into practice. We are going to construct the canonical Burr chatbot from absolute first principles. We're going to write the code, wire up the graph, and actually watch the state machine breathe life right into a continuous conversational loop.
Okay, so here's the fundamental question we really have to answer. How do we build a conversational loop that literally never loses its memory? If you've ever hacked together a basic script to ping a large language model, you already know the massive headache here. Standard LLM scripts process a single turn, and then, poof, they forget everything. And if you try to wrap them in a standard Python while loop, you either lose the context entirely, or you end up hacking together these messy global variables just to hold the history. Burr actually solves this problem by moving the conversation out of hidden application memory and placing it squarely inside an explicit state machine.
Let's break down why we absolutely must put our chat history into Burr's immutable state object. It really boils down to this. The state is the only thing that has reliably checkpointed across every single conversational turn. By making chat history a formal state variable, it automatically powers the built-in local tracking UI, which lets you visually inspect the chat log at any precise moment in time. It even enables you to rewind and replay the exact state of a conversation for debugging. A runtime prompt provided by a user is fleeting. It exists only for a split second at execution time. But the chat history? That's a durable record that lives safely in state.
So the crucial point is this specific architectural cadence. It's the recurring metaphor for literally everything you will build in Burr. Every single action follows this exact pattern. You read the declared state, you compute your logic, like calling an external API, you update the immutable state with those results, and then you explicitly transition to the next action. This pattern never changes, whether you're building a tiny toy chatbot or a massive enterprise simulation.
Action 1. Human input.
Let's look at the anatomy of our human input function. Notice the decorator right at the top. We are strictly declaring that this action reads absolutely nothing from the current state, but it is authorized to write to two specific keys, prompt and chat history. The function itself receives the immutable state object, along with an external runtime parameter called prompt. Now, this parameter isn't coming from some database. It's being supplied dynamically by the client at the exact moment of execution.
And here is exactly how that action wraps up. It's a brilliant illustration of Burr's whole immutable state philosophy. We aren't just modifying the existing state in place. Instead, we call state.update to bind the new runtime prompt into the durable state, and then we call .append to safely push the formatted user message directly into our chat history array. The action then returns a brand new state object, perfectly preserving our audit trail.
Action 2. AI response.
Now, our AI response action has a totally different contract. Notice the action decorator this time. It explicitly demands that chat history must exist in the state before it's even allowed to execute. If it's missing, Burr will actually fail the execution graph statically before the code even runs. When the function does execute, it pulls that durable conversation record out using state/chat history and feeds that entire context window straight into the LLM client. Once the LLM fires back its generated text, the AI response action finalizes its work using the exact same pattern we just saw. It updates the state with the raw text response, and it appends the newly formatted assistant item right into the running chat history. The state updates, and just like that, the action is complete.
Building the cyclic graph.
Let's move on and see how this builds into our state machine. The logic here is incredibly straightforward but highly consequential. The application executes the human input action. It unconditionally transitions to the AI response action, and then, this is the critical part, it cycles straight back to the human input action. This creates a true, continuous cyclic graph.
To actually express that loop in code, we use the with transitions method on the application builder. We just pass in simple tuples outlining the origin node and the destination node. Human input flows to AI response, and AI response flows right back to human input. There is absolutely no hidden framework magic going on here. The routing logic is explicitly declared right in front of you.
Halting and resuming execution.
Here's the catch, though. If you just tell this graph to run as is, you are going to hit a massive deadlock. The system processes the human input, generates the AI response, loops back to the human input node, and then it just freezes forever because there's no new prompt waiting for it. The deadlock danger breakdown here represents exactly why this happens. To solve this, Burr requires us to intercede with explicit control. We have to introduce a mandatory halting condition for each turn, allowing the state machine to safely pause execution and wait for the human to type a new message.
So here is how we execute that safely. We call app.run. But notice we pass in halt after for AI response. We are instructing the framework to process the graph, but to suspend operation the exact moment the AI completes its turn. Also, check out that inputs dictionary. That is exactly where we inject the runtime prompt into our human input action. When this line of code finishes executing, the application gracefully yields control, and our final state contains the perfectly updated array of both the user and assistant messages.
Provider independence in Burr.
Now, what's really interesting here is the equal distribution of providers. While our conceptual examples might assume an OpenAI or an Anthropic call is happening inside the compute step, the Burr orchestration layer fundamentally does not care. It doesn't require a specific vendor compute provider at all. You can utilize the documented Amazon Bedrock integrations, route through a LangChain wrapper, call a local model on your own hardware, or honestly, even just use a mock function that returns static text for testing.
Let's definitely reinforce a few practical developer cautions here. Burr is a state orchestration layer. It is not an LLM wrapper. The actual compute step, the network call to an AI model, is entirely external to the framework's core responsibility. As a developer, avoid getting distracted by vendor hype or rapidly changing LLM SDKs. Focus instead on the integrity of your state machine. Whether you are using a legacy foundational model or an incubating local tool, the core Burr pattern stays the exact same for sure. Read declared state, compute externally, update state immutably, and transition explicitly.
So we have successfully built the canonical conversational loop from absolute first principles. But a chatbot that only talks? That's really just the beginning. The real power of an explicit state machine emerges when the AI can actually take action. So, as you review this architecture, ask yourself, with a perfect memory loop established and explicitly declared transitions, how will you wire your own custom APIs, database queries, and custom tool calling directly into this cycle?
Let's jump right into this explainer. We are taking a basic single-turn chatbot and escalating it into a highly complex explicit state machine. And we're doing this by tapping into the routing mechanics of Apache Burr. Moving from simple prompt response loops to autonomous multi-agent systems, it makes the architectural requirements for state management and deterministic control flow just exponentially more demanding. So we need to look exactly at how Burr handles routing, retrieval-augmented generation, and tool execution patterns to make these systems genuinely reliable in production.
Notice the architectural contrast here. On the left side, we've got a trap that's super common in early generative AI applications, implicit routing. This is where you have massive, hidden if-else blocks buried deep inside a single large language model call, or just totally obfuscated inside some giant wrapper function. It is an absolute debugging nightmare. When it fails, you literally have no idea why. But then, on the right side, we see the Apache Burr approach, explicit routing. We're replacing that black box branching with highly inspectable, explicit transitions between distinct nodes. The control flow is pulled entirely out of the prompt and placed right into the state machine graph.
Section 1. The Routed Assistant Pattern. We're going to extend our chatbot with explicit intent.
Okay, so the first major step in scaling up our architecture is moving from a simple conversational loop to a routed assistant. We do this by adding a router to explicitly direct incoming user queries before the main generation step even happens. Just take a look at this Python snippet. Here, we've got an intent classifier or a route query action. Notice the strict contract defined by that @action decorator? It explicitly reads the prompt from the immutable state, and it explicitly writes a compact routing field called intent. We aren't generating some massive final response here. No, we're simply taking the normalized question, having a lightweight model or classifier figure out what the user actually wants, and then writing that single intent string straight back to our state variable.
So what's the crucial takeaway here? Well, by writing that single intent to the state, our application definitively chooses the next execution path without relying on any hidden LLM magic mid-cycle. Think about it. If the intent evaluates to greeting, we transition directly to the answer directly node. Need facts? Boom. It routes to retrieve context. We can route execution to a tool, ask the user for clarification, or branch off to produce a summary. Because this logic is governed by explicit Burr transitions, using conditions that simply evaluate that intent string, the execution is entirely deterministic and, best of all, fully auditable.
Moving right along to Section 2, Orchestrating RAG Workflows. This is retrieval-augmented generation functioning as a state machine.
Let's apply this explicit routing to complex data pipelines. This sequence beautifully illustrates RAG as a clean pipeline when you model it in Burr. Rather than a tangled monolithic script, each step is a discrete action. Step 1. Embed query. Reads the user's prompt and writes a vector to the state. Step 2. Retrieve documents. Reads that vector and writes a list of raw documents. Step 3. Rank context. Reads those documents and writes a filtered, highly relevant context array. And finally, step 4, generate answer. Reads both the prompt and the refined context to write the final response. Every single action explicitly reads and writes specific declared state fields. If your pipeline hallucinates, you don't panic. You just look at the exact state between step 2 and step 3 to see precisely what documents were retrieved.
Now, this brings us to a massively important architectural advantage: framework agnosticism. Burr does not prescribe a specific retrieval library. Whether you're using a raw vector database, DeepSet's Haystack, or just some custom Python code you wrote, Burr simply orchestrates the stateful flow around whichever retrieval stack you prefer. It acts as the rigid control plane, managing the cycles and the state, while your chosen tools handle all the heavy mathematical lifting.
Section 3, the tool execution pattern. Let's talk about managing external side effects. How do our models safely interact with the outside world? Whether that's querying a live API or modifying a database, managing external side effects is absolutely critical for reliability. A huge anti-pattern in AI development is letting a model decide to call a tool, execute the API request, and format the response all in one massive unobservable step. Look at this state field lifecycle instead. In Burr, a routing action first decides what to do, writing the tool name and the specific tool args to the state. Then, a dedicated tool action actually performs the external call. Following that, an observation action explicitly captures what happened, recording it into a tool result field. Only then does a final response action come in to explain that result to the user.
Let's look a little closer at that observation action. This is a dedicated state machine node, and its sole job is to safely record external side effects or API returns back into our mutable state. Keeping these side effects perfectly contained in a well-named observation action guarantees that the entire execution graph remains completely auditable. Think about it. If a third-party API goes down and returns a 500 error, your application doesn't just crash mysteriously. Instead, the observation node records the failure right into the state, allowing your transition logic to route gracefully to an error handling node or maybe even ask a human for help.
Section 4, Beyond LLMs. Here, we'll cover general routing and framework agnosticism.
To really grasp Burr's architectural power, you have to realize that it is a robust, general state machine framework that just happens to be incredibly useful for AI systems. Look at how universal this pattern is. You can use this exact same framework to route a simulation step, advancing to the next simulated event based on a state variable. You can use it in a stateful game to fork a what-if scenario. You can manage a hyperparameter tuning trial by having a transition choose to try the next configuration. Or in a dynamic business workflow, a transition can branch straight to failure analysis. And get this, you can do all of this without making a single machine learning model call. The transition logic simply evaluates the immutable state and decides the next node. It's like a perfectly organized puzzle.
Section 5, the Golden Design Rule, Inspectability through Explicit Transitions.
All of these patterns we've covered, the routed assistant, the RAG pipelines, the tool execution lifecycles, they all culminate in one overarching architectural philosophy. Explicit routing makes debugging incredibly straightforward. When a wrong answer or a bad workflow outcome happens, you don't have to sit there and guess what the model was thinking. No, you just open your local Burr Telemetry UI and you inspect. You look at the intent field that was written, you look at the exact retrieved context array, you check the specific tool result or those simulation metrics. Because every decision, every piece of context, and every fired transition is permanently logged in the tracker, you have a perfect point-in-time snapshot of your application's state.
So I want to leave you with this golden rule. Model important decisions as transitions, not as invisible branches inside a single oversized action. Think about pulling that control flow out into the light. If you want to build truly resilient applications that don't just work in a prototype notebook, but actually survive in complex production environments, how will you redesign your current monolithic functions to expose their hidden transitions?
Segment 14, Human-in-the-Loop Workflows and Review Loops in Apache Burr. Let's dive right into a seriously critical design pattern for production AI. If you're building generative AI apps that actually interact with the real world, you literally cannot afford to skip this. We're looking at exactly how Apache Burr, which is an incubating project at the Apache Software Foundation, enforces these crucial review loops using explicit state machines.
So what happens when an autonomous agent makes a massive mistake on an irreversible action, like firing off an email or making a big purchase? We've got to start with this cold truth. Fully autonomous systems pose massive risks, especially in sensitive enterprise domains. Think legal analysis, financial forecasting, or external corporate comms. What happens if an AI hallucinates and unilaterally decides to send a completely destructive email to a top client?
or commits to an irreversible financial transaction? No way. If your agent's reasoning loop is totally unchecked, you've got a massive operational liability on your hands.
This brilliantly illustrates why we've got to move away from the illusion of full autonomy and get real about deterministic control. Look at the left side. That's your traditional black box agent loop. It's completely opaque, the internal state is totally hidden, and execution is unilateral. It essentially relies on a fragile while loop that is an absolute nightmare to audit. Now, over on the right, we've got the inspectable state machine. In Apache Burr, this means explicit declarative state, safe halting checkpoints, and strict human gating. You're defining exactly what the app is allowed to do, and more importantly, exactly when it must hit the brakes and wait for human permission.
Moving right along to visualizing the review loop, the email assistant anchor. To really ground this, let's use a concrete email drafting assistant as our anchor example. Think of this workflow exactly like a high-tech assembly line. The state transitions sequentially through these explicit actions. First, step 1, process the input. Then, step 2, the LLM takes that context and formulates a draft. But before it can actually hit send, the assembly line physically stops for step 3, human review and processing feedback. A real human operator reads the draft, provides their input, and only then does it move to step 4 to revise that draft, and finally, step 5, yielding the final result. In an enterprise system, this specific sequence isn't just a friendly suggestion. It has to be mathematically guaranteed by the framework itself.
So how do we actually do this? Let's look at halting execution and implementing interruption in Burr. How does Apache Burr securely stop that assembly line? Well, it's not by using some generic sleep function or a super messy while loop break. It uses halt before. By passing this explicit halt before command, Burr pauses the state machine exactly before an action that requires human input, like clarify instructions or process feedback. When it hits that exact point, Burr securely saves all its progress to your database and completely releases the backend server thread. The application basically goes to sleep, just hanging out until a human foreman gives the green light. And that wait could be minutes, hours, or, if they went out for a long weekend, even days later.
And the natural companion to that is halt after. Conversely, halt after ensures the application safely idles out once a terminal action actually completes, something like computing the final result. This is super important because it guarantees that the loop doesn't accidentally restart itself or just spin out of control. It keeps the execution trace closed and ensures the state is fully recoverable right at that precise endpoint.
Let's transition over to the Python implementation and see how we actually code the workflow.
Let's see how this builds out an actual Python code using Burr's application builder. The absolutely crucial point here is that you trigger the agent with these explicit halt commands right when you call the run method. Look at this snippet, app.run, and then you pass in halt before equals process feedback and halt after equals final result. By just passing these simple arrays into the execution call, the Burr backend physically prevents the LLM from unilaterally taking a sensitive action. The server thread just runs the nodes up to the feedback step, safely serializes that state straight to the database, hands the draft payload back to your user interface, and then totally frees up your server to handle other requests.
Then, when the human eventually does provide their feedback via front-end UI, a brand new HTTP request hits your server. You reload the application from the database and resume from that exact checkpoint using this line, action result state equals application.step inputs equals feedback user input. The framework literally injects the user input directly into the pending step, securely bypassing any normal state transitions. Boom! The graph execution just resumes flawlessly with the human's corrections right there in hand. That brings us to state persistence and resumption. To actually make this human-in-the-loop delay work, especially if we're talking about long periods of time, that state absolutely must survive while it's waiting for the human. If your server restarts, you really can't afford to lose the LLM's entire reasoning context. This table breaks down the super elegant handoff between a modern stateless backend, like a FastAPI server, and Burr's explicit persistence layer. Your web API stays entirely stateless. It's just there to catch the HTTP request and yield control. Meanwhile, the Burr application is stateful. It uses built-in persisters, plugging right into SQLite or PostgreSQL to reliably save and load those checkpoints. This is huge because it means you can horizontally scale your web servers without ever sweating about losing the active memory of your AI agents.
Because Burr treats state as an explicit, immutable, and fully inspectable dictionary, nothing gets lost in the ether. Just take a look at these explicit state elements natively captured by the framework. You've got the initial draft, any clarification answers, the exact string of human feedback, the Boolean approval flag, and of course the final revised result. every single one of these elements is permanently recoverable and auditable. Whether you're using Burr's local tracking UI or connecting directly to your database, an administrator can see exactly what the LLM generated, precisely what the human corrected, and exactly what actually got sent out.
Now, let's look at this through the lens of an auditable production architecture. Let's pull this all together because we really need to understand why this architectural pattern is essentially mandatory for enterprise production. This isn't just about making things function. It's about making them compliant and mathematically safe. The advantages listed here completely rewrite how AI is deployed. Think about it. The human decision is no longer some hacked-on wrapper step managed by messy API endpoints. It becomes a fundamental, fully traced node living right inside the state machine itself. This completely eradicates the need for informal, external wrapper logic. Your high-stakes actions are mathematically gated by the graph. And because every single step is recorded by the Burr tracker, you get 100% reproducible execution traces. Meaning, if an agent somehow goes rogue, you can rewind the state to the exact node and debug it perfectly.
The official documentation really hits the nail on the head with this quote. The state is persisted, the UI or API returns control to the user, and a later request resumes from the save checkpoint. This simple dynamic fundamentally transforms how you build reliable, interruptible AI web services. And the best part? You're doing it without keeping really expensive compute resources locked up. You aren't forcing an LLM to just sit there idling, eating up memory while a human takes their sweet time reviewing a draft. The entire system is completely decoupled and perfectly efficient.
So, as we wrap up this explainer, I want to leave you with this provocative question. How will explicit state and proper human-in-the-loop review loops transform your most sensitive mission-critical AI deployments? Once you step away from the sheer unpredictability of black box autonomy and actually embrace inspectable, state-driven execution, you unlock a level of safety and deep observability that enterprise systems literally demand. I highly encourage you to think about how this framework can bring some much-needed order, safety, and transparency to your very next major AI deployment.
Welcome to segment 15 of our Apache Burr Explainer. Today, we're diving into streaming actions, protocol, state safety, and low-latency interfaces. Look, as we build these increasingly complex LLM applications, we all know users absolutely expect to see those partial responses streaming in, token by token, right while the model is still thinking. But here's the catch. Explicit state machines, they demand deterministic, final state updates to actually function properly. So today, we are going to unpack exactly how Apache Burr reconciles these two seemingly opposing requirements. Let's get right into it.
Here is our agenda for today. We'll be covering the latency versus state dilemma, the core streaming protocol, writing streaming actions, consumption and safety, routing intermediate nodes, and finally, FastAPI web deployment.
Section 1. The latency versus state dilemma. Speed versus determinism. So modern AI demands low latency, for sure. But if you're building a reliable agentic workflow, you literally cannot afford to have a half-finished sentence permanently overwrite your agent's core memory, right? So the crucial question we have to ask is, how do you stream non-deterministic output without corrupting your deterministic state? Think about it. If an LLM just suddenly drops the connection halfway through and you've been blindly appending every single partial token directly to your backend database, well, your state graph is fundamentally broken. We absolutely need a way to sever the act of streaming to the user from the act of updating the system state.
And this is where Burr steps in. Burr elegantly solves this by treating streaming entirely as a latency layer. It's a user experience layer that sits completely independent on top of the rigorous state transition model. In the Burr architecture, streaming doesn't alter that fundamental state machine contract at all. Instead, it just provides a specialized pathway for intermediate chunks to flow directly to a browser, a terminal, or maybe a notebook as they arrive. And it does this while completely bypassing the persistent state vault until the generation is totally finished.
Moving on to Section 2, Burr's core streaming protocol, holding state securely.
Okay, so how does it actually do this? Burr orchestrates this separation through a very strict token flow protocol. When your Python generator is actively running, it's emitting tuples. Now, the first part of that tuple is the chunk, but the second part, the state update, must strictly be none. You yield the chunk and you yield none. It is only on the absolute final yield that the fully accumulated string is passed alongside the newly updated state object, and only then does it trigger the lifecycle hooks and the database commits. It's a really brilliant way to keep everything safe.
Section 3. Writing streaming actions. Decorators versus classes. When you're actually writing these actions, you basically have two choices. You can use the decorator form for simpler functions or the class-based pattern. The class approach cleanly isolates the stream generation in a stream run method from the actual state mutation in an update method. The streaming action decorator, that is fantastic for your quick, functional generator implementations. But if you have highly complex logic, say where you really want to cleanly isolate the networking complexity of stream consumption from the deterministic logic of the state mutation, well, the streaming action base class is incredibly powerful for that.
Let's look at the syntax here. By explicitly yielding your chunk, like a dictionary with a response delta, alongside none for the state, you guarantee that Burr waits to commit the durable state update. You're basically sending a very clear structural signal to the Burr framework. You're saying, hey, I'm still working here, do not fire any lifecycle hooks, and absolutely do not write this to the database yet. It's only that final yield that actually executes the state append, like appending the completed message to the chat history.
Next up, Section 4, Stream Consumption and Safety, extracting the stream safely.
Now, once those actions are written, we have to consume these streams safely, right? Depending on your setup, you'll use these specific APIs to return a container object. That object lets the caller iterate over the intermediate output before retrieving the final state. So if you're in a synchronous environment, you trigger execution with stream result, which hands back a streaming result container. But for high concurrency environments, you'll just mirror this exactly with a stream result and an async streaming result container. These essentially act as highly optimized cached iterators.
And here is why this matters immensely. As you iterate through that container, Burr is enforcing strict, delayed execution guardrails, delaying hooks and persistence until the iterator actually completely eliminates the risk of fragmented data corrupting your database. So things like your OpenTelemetry spans, your local tracker UI updates, and your SQLite or Postgres persisters, they all just sit completely dormant until that final state is safely and fully assembled.
Section 5. Routing intermediate stream nodes. Streaming mid-graph.
But wait, what happens if a streaming action is not the final exposed node in your application's graph? What if it's just one reasoning step in a much larger multi-node agentic workflow? Well, Burr handles this effortlessly. Say you have a draft response node. Burr will automatically stream that intermediate action to the user, exhaust the stream internally to finalize the state, and then seamlessly transition to a silent or terminal node like store response or route next without missing a beat. So stream to the user and terminal graph result are related, but they don't always have to be identical.
And finally, Section 6, FastAPI and Web Deployment, Scaling to the Browser. Let's connect all these state-safe streaming concepts to real-world web deployment using a modern framework like FastAPI. Your FastAPI endpoint can simply wrap Burr's container in server-sent events, or SSE. This pushes chunked updates to the front end, while Burr handles the workflow state natively in the background. Because Burr's database persisters handle all the heavy lifting of state memory, your FastAPI server remains entirely stateless. And you know what that means? You can scale horizontally across serverless environments or Kubernetes clusters with zero friction.
Looking closely at this deployment pattern, it really proves a key point. Streaming does not remove the need for persistence, tracking, or cancellation handling. It simply acts as an elegant UI layer on top of the same rigorous graph model. The FastAPI server takes that inner async generator from Burr and formats it into standard server-sent events payloads. It prefixes the data chunks with a data identifier, formats them as raw JSON strings, and ends them with 2 new line characters. This allows a front-end framework like React or whatever you're using to consume the stream perfectly frame by frame.
So, summing it all up, mastering this protocol ensures your users get the lightning-fast speed they expect without ever sacrificing the enterprise-grade state safety that your infrastructure absolutely demands. By forcing developers to explicitly separate the non-deterministic flow of tokens from the deterministic state machine updates, Apache Burr gives you the architectural clarity needed to bridge the gap between fragile AI scripts and truly robust web services. Leaving you with this to consider, as you build your next agent, how will separating latency layers from strict state transition logic redefine your system's resilience?
All right, let's talk about that moment your application goes from being a neat little prototype to a heavy-duty production-grade system. When you're building AI agents or complex state machines in Apache Burr, eventually you are going to hit a wall, and that wall is usually blocking synchronous tasks. Today, in this explainer, we're mapping out the shift from simple sequential graphs to powerful asynchronous flows. We'll look at fanning out with parallel MapReduce architectures, and crucially, how to secure those parallel branches with explicit reliability boundaries.
Here is our agenda. We've got async execution and I/O, map-reduce parallelism, practical scenarios, child state boundaries, operational maturity, and finally, platform boundaries.
Section 1. Async execution and dependencies. Breaking I/O bottlenecks. So we have to start with the absolute biggest bottleneck in AI applications, input/output. When your state machine hits an external network service, say an LLM API or a remote database, blocking the main thread literally kills your throughput. But Burr provides a mechanical API switch to solve this. For local CPU-bound tasks, you use standard synchronous flows with run and step. But for network calls, you switch to their non-blocking variants, rrun and astep. This simple swap allows your server to handle thousands of concurrent agent workflows without locking up the whole system while you wait for tokens to generate. But here's the catch, and it's a big one. Flipping that switch to async isn't some magic bullet. Your application has to be async all the way down. Because think about it, if your action uses a blocking synchronous database driver inside an async flow, you're still going to block the event loop. Unlocking the real value of async absolutely depends on using async-compatible dependencies, like AsyncDB drivers or async LLM clients, inside the execution itself.
Section 2. Map-reduce parallelism and expressing branching logic. Now, Burr actually gives you specific primitives, so you don't have to hack together your own branching logic when you want to run things in parallel. You can use map states to run the exact same action across a bunch of different state payloads. Or you can use map actions to run entirely different actions against one single state. If you need massive fan-out, well, map actions and states gives you the full Cartesian product. And for those really complex subtasks, Runnable Graph lets you execute entirely reusable subgraphs over those independent branches.
Taking this from theory into actual Python code, we can see how simple this is. A parent workflow can use map actions to branch out and test multiple LLM prompts completely in parallel. And then, a reducer step just safely synthesizes those diverse responses, grabbing the parallel outputs and cleanly merging them right back into a single, cohesive parent state.
Section 3. Practical scenarios for AI and data science fanout.
This is exactly how modern LLM engineering works in the real world. I mean, you rarely just ask one question and blindly trust the very first answer, right? You rely on fan-out. You might try multiple prompts against one model to see what sticks, or test multiple models against a single prompt. You could run several distinct tools in parallel, or simultaneously fire off a semantic vector search and a live web search. Then your synthesis action acts as the reducer, choosing the absolute best evidence from all those branches to formulate the final answer.
But hey, it's not just about language models. Map-style branches are absolutely vital for data science and non-LLM workflows too. You can use this to run massive Monte Carlo simulation scenarios concurrently. You could compare different hyperparameter configurations, evaluate alternative feature transformations, or even fork a stateful planning system, like a game, from one checkpoint into several possible futures to figure out the best move. Now, usually, parallelism just creates a massive debugging nightmare. It becomes this opaque black box where things fail silently, but Burr's tracking UI makes every single child and sub-application run completely visible. You don't just see that a parent task started and finished, you can inspect the exact fan-out graph. You can literally click into specific branches to see precisely what prompted a failure or a success. It's a real game changer for visibility.
Section 4. Child state and merge boundaries, securing the perimeter.
So when you've got multiple branches firing off at once, if they all try to write to the exact same state key, like a generic results key, at the same time you are going to get a nasty race condition. That's why we introduced the child state boundary. This is a strict rule. Parallel branches must have explicit ownership of specific state keys. Unless you explicitly model the pattern, you have to define explicit merge behavior to prevent these branches from corrupting your application state.
The mindset shift here is so important. You really have to treat every single child branch or sub-application like its own perfectly clean, isolated little workspace. It does its job, it mutates its own local state, and it only interacts with the parent application by handing a structured payload back up to the reducer. The reducer is essentially the gatekeeper, deciding exactly what gets to enter the parent state.
Section 5. Operational maturity and handling partial failures. Look, interleaved parallel streaming, ray integrations, sub-applications, these are incredibly powerful, but they're advanced and still evolving. So before you start relying on production fanout, your team absolutely has to run through this operational validation checklist. You've got to validate your cancellation behavior. You need graceful failures and hard timeouts so a stuck network call doesn't hang your whole operation. You have to define explicit retry semantics, make sure you clean up child state, and confirm that everything is observable. Which leads us to this massive paradigm shift. Partial branch failure should be designed as a first-class state outcome, not discovered by accident. In parallel workflows, one branch failing out of 10 isn't an unhandled exception that should crash your app. It's a valid expected state outcome. Designing your reducers to actually handle partial branch failures, that's how you build truly resilient applications.
Section 6. Platform Boundaries. Comparing Burr versus Durable Orchestration.
We need to draw a really strict boundary here to avoid any architectural confusion. Apache Burr is fantastic for in-process Python-centered state machines. It persists state and resumes workflows perfectly through your configured database. But compare that to durable platforms like Temporal. Burr does not inherently provide worker supervision, automated process restarts, or infrastructure-level fault tolerance. You still have to design your own job queues and retry handling, unless you deliberately choose to wrap Burr inside a durable orchestration platform. Let's pull this all together with some core design heuristics. Rule 1. Use sync flows for clarity while you're just learning the framework. Rule 2. Switch to async execution when external I/O would otherwise block your server. Rule 3. Use map-style parallelism when the independent subtasks can be safely decomposed and recombined. And finally, Rule 4. Keep your Burr graph readable. Even when execution gets highly concurrent, the logic needs to remain totally transparent.
So, moving from linear scripts to parallel, asynchronous state machines, it is a massive upgrade, but only if you manage it with extreme rigor. So I want to leave you with this thought. Think about your current pipelines. If your parallel workflows fail silently today, how will enforcing explicit state boundaries and treating partial failures as a first-class outcome redefine your team's operational resilience tomorrow?
Let's dive right into segment 17 of our explainer. We're looking at how to transform messy, instrument-heavy code into sleek, enterprise-grade AI applications. You know, in modern stateful AI development, one of the fastest ways to completely ruin a brilliant piece of architecture is to tangle your core decision-making logic with a massive web of telemetry, logging, and database tracking. So today, we are focusing on how Apache Burr solves this through a really clean, decoupled approach.
We've got a packed agenda today. We're covering what lifecycle hooks actually are, mapping out the action timeline, building custom instrumentation, hooking up OpenTelemetry, comparing local versus production observability, and wrapping up with some absolute must-know best practices.
All right, part 1. What exactly are lifecycle hooks? So we've got to address a massive developer pain point here. You know that absolute nightmare of burying logging, metrics, and tracing logic right in the middle of your core action code? Yeah, there is literally nothing quite like the misery of waking up to a broken production database just because someone fat-fingered a print statement or a trace ID formatter inside a critical AI decision loop. No way. So the solution? Lifecycle hooks. Think of these as Burr's dedicated extension surface. They let you cleanly intercept application events, like recording trace IDs, costs, request IDs, sequence IDs, and queue emissions, and you do it completely out of band. Because they run around your action execution, your core business logic stays pristine. It stays totally focused on making AI decisions, while the hooks just quietly handle the operational tracking in the background. Moving on to Section 2, the action execution timeline. To really master these hooks, we need to map out the exact execution timeline. It's a highly deterministic ordered sequence. Before your action even touches the state, boom, the pre-step hook fires. Then the action runs, the result is computed, and that immutable state gets updated. Only after that new state is fully generated does the post-step hook fire, which is then followed by the framework actually selecting the transition to the next action. Understanding this exact sequence is absolutely crucial because it tells you precisely what data your hook has access to at any given microsecond.
Now, keep in mind that Burr offers both sync and async hook variants. The real game changer here is that your hook design has to perfectly match the surrounding application mode. So if your enterprise app is heavily async, say you're using an asynchronous web framework like FastAPI, you absolutely must use asynchronous hooks. You definitely don't want a blocking synchronous logging hook to accidentally freeze up an otherwise highly concurrent async event loop. That would be a disaster.
Okay, section 3. Let's build some custom instrumentation and look at some practical examples.
This is where the theory gets super practical for your daily development. Here's a highly condensed little snippet of a logging hook in Python. By inheriting from the post-run step hook class, this code cleanly intercepts the end of an action. So instead of forcing every single developer on your team to remember to log their actions, which, let's face it, never happens, this one single hook automatically writes structured JSON. It pulls sequence IDs, app IDs, and error metadata for every single action across your entire state machine.
Check out this next snippet. It shows a metrics hook seamlessly incrementing enterprise metrics. We're talking about tracking token counters and action latency. By dropping counter.inc and record latency right into this post-step hook, you're guaranteeing that your APM dashboards reflect exactly how much time and money each LLM node is eating up. And it's entirely separated from your prompt engineering logic. You could even take this exact same architecture and build a queue hook, instantly pushing downstream events to Kafka or RabbitMQ the second an important step finishes.
You can also build an audit hook. Notice how this one inherits from pre-run step hook. Before the model even fires, this hook is capturing model names, estimated costs, and high-level safety flags. The critical takeaway here? You can build this to capture strictly metadata, completely free of embedded secrets or sensitive PII that might be floating around in the broader state. That ensures your telemetry stays totally privacy-aware.
And you know, hooks aren't just for logging. You can actually use them for visualization too. Take this slow down hook. When you're running agent simulations, those loops can execute in milliseconds, which is way too fast for a human to follow. So this hook intentionally injects a time.sleep delay into rapid loops. That way, developers can actually watch the UI updates sequentially during live demos or debugging sessions. Pretty neat, right?
All right, section 4, OpenTelemetry and APM. Let's talk cloud observability. Now that we've got local hooks down, let's scale up our visibility. We're going to connect Burr to OpenTelemetry and application performance monitoring platforms. Setting use OTel tracing equals true inside your application builder is hands down the simplest path to wiring up the OpenTelemetry bridge. Literally, by just flipping this Boolean, you instantly connect Burr's entire lifecycle to your broader enterprise tracing infrastructure. Whether that's Datadog, Langsmith, Traceloop, or any other OpenTelemetry compliant backend, you're good to go.
Inside your actions, you can dig even deeper. You can use the _tracer API alongside provider instrumentation like OpenTelemetry. This lets you capture granular spans, which, if you aren't familiar, are basically just timed units of work, like a specific database query or a raw model provider API call. You capture these right next to your broader Burr action spans. It gives you incredible micro-level visibility right inside the macro-level state machine.
Moving to Section 5, Local versus Production Observability.
It is absolutely vital to understand the production observability distinction here. There's a massive difference between inspecting a local run on your laptop and correlating data in the cloud. Local tracking, like seeing the Burr UI spin up on port 7241, is phenomenal for developer inspection. It answers the question, what did the state machine do in this specific session? But OpenTelemetry, that's for production. It answers the heavy-hitting enterprise question, how did this specific user request move through our entire distributed architecture across multiple microservices?
Let's trace this visually to see how OpenTelemetry actually ties the whole shebang together. Say a single FastAPI request enters your web service. That triggers Burr, which emits spans mapping your action graph. Inside those actions, a vector database emits a retrieval span, followed by the LLM emitting a model provider span. And finally, the Burr persister emits storage spans as it saves the state to PostgreSQL. OpenTelemetry magically binds all 5 of these distinct events into one cohesive trace for your incident response team. It's brilliant.
Finally, Section 6, Best Practices and Enterprise Guardrails.
Before we wrap things up, we really need to lay down some strict enterprise guardrails to ensure your system stays resilient and mathematically predictable. Please, burn this rule into your memory, because it's the most common mistake engineers make. Never, ever rely on hook ordering for critical business rules. If a decision changes the trajectory of your application, it explicitly belongs inside your actions, inside your conditional transitions, or stored in your explicit state parameters. Hooks should strictly remain passive observers and operational reporters.
Because custom hooks run directly alongside your core application lifecycle, you've got to treat them with respect. You have to ensure they are deterministic and heavily tested to prevent accidental crashes. They need to be extremely lightweight too. I mean, you really don't want a heavy logging hook adding 500 milliseconds of latency to every single action step. And, where practical, make them idempotent.
That way, if a hook fires twice during a retry, it doesn't totally corrupt your telemetry backend. I'll leave you with this provocative thought to challenge how you architect your next agent. Think about your current codebase. If your AI crashes in production tomorrow, does your architecture cleanly separate its decision-making logic from its operational telemetry? Or are they just a tangled mess? Truly mastering that separation, using lifecycle hooks and OpenTelemetry, is the ultimate hallmark of an enterprise-grade AI system. Apache Burr's Bring Your Own Tools integration philosophy really solves one of the biggest headaches we have in generative AI. I mean, the ecosystem is absolutely exploding right now with specialized tools for prompt engineering, retrieval, model orchestration. But tying them all together reliably, that is incredibly hard. So in this explainer, we're diving into how Burr serves as the ultimate explicit orchestration layer for your favorite tools.
Here is our architectural blueprint for today. We're going to cover the integration philosophy, bridging Hamilton and Burr, LMMs and retrieval frameworks, interfaces, schemas and scale, and finally, the visible state machine.
Let's jump right into the integration philosophy. Bring your own tools. This is genuinely the core ethos of the whole project.
The absolutely crucial point here is that Burr does not force you into a specific LLM abstraction. Actions are literally just ordinary Python. You know how some frameworks force you to rewrite your entire codebase into their proprietary domain-specific languages or maybe some obscure YAML configurations? Well, Burr takes a massive step back. It assumes you already know how to query an LLM or fetch data from a database. Its only job is to be the control layer, the explicit state machine orchestrating those regular Python functions.
So what actually is an integration in this ecosystem? It's simply a visible, modular piece of your state machine. There's no hidden magic here. When we say Burr integrates with a tool, it usually just means Burr provides a specific action class or helper function that securely wraps it. The tool does its specific task, like retrieving a document, while Burr handles all the heavy lifting, managing the overarching graph structure, persisting data to a database, tracking telemetry, and deciding where the application transitions next. This is a game changer because it means you are never locked out of debugging your own application.
Moving right along, let's talk about bridging Hamilton and Burr, going from DAGs to cycles. We're looking at Apache Hamilton first because it's historically and architecturally fundamental to Burr's creation. They actually share the same original creators.
This comparison really highlights how Burr acts as the cyclic harness wrapping around Hamilton's strict linear data transformations. Hamilton is incredible at building directed acyclic graphs, or DAGs, for rigid stuff like feature engineering and deterministic math. But a mathematical DAG can't loop. It flows in one direction. AI agents, on the other hand, fundamentally require loops, right? They need to observe, act, and reason in a continuous cycle. So Burr was designed specifically to be the stateful, cyclic harness that wraps around those linear Hamilton graphs.
Just look at this Python snippet. Inside a standard Burr at action, you can delegate a deterministic transformation task directly to a Hamilton driver action. Hamilton executes the complex mathematical pipeline, returns the final result, and then Burr safely captures that output and writes it right back to the global application state. You literally get the deterministic precision of Hamilton wrapped safely inside the autonomous looping logic of Burr. It's the best of both worlds.
All right, let's move to the brains of the operation, LLMs and retrieval frameworks. We'll look at LangChain, Haystack, and Bedrock because let's be real, you aren't building AI without models and context.
With LangChain, it works right out of the box, since Spur actions are just Python. But there is a massive gotcha you need to be aware of. You absolutely must keep unserializable chain or client objects strictly as runtime inputs or action configuration. Why? Because Burr's superpower is saving your state to durable databases like PostgreSQL or SQLite so your application can pause and resume. If you accidentally store a live active LangChain client connection inside Burr's durable state, the database serializer will crash. The golden rule here, keep your data in the state and keep your API clients strictly as runtime inputs.
Next up is Haystack. This is seamlessly brought into Burr to give your RAG applications interactive state capabilities. DeepSet Haystack is a huge player in the retrieval augmented generation space, and Burr supports it beautifully through native wrapper modules.
You can see here how Haystack action explicitly enables a pipeline inside an action pattern. You don't have to rewrite your existing Haystack prompt builder or retriever at all. Burr instantly turns it into a compliant node on your state machine graph.
Actually, taking it a step further, you can even convert an entire linear Haystack pipeline directly into a Burr graph using the Haystack pipeline to Burr graph utility. Now keep in mind, this specific path is still marked as experimental, but think about how powerful this is. If your team has spent months building a linear RAG pipeline in Haystack, you can automatically compile it into a Burr state machine graph. Bam! Instant local telemetry UI, visual debugging, and SQLite persistence, all without throwing away your core retrieval architecture.
For the AWS users out there, the Amazon Bedrock integration provides provider-specific action helpers directly inside your state machine. Burr gives you first-class classes like Bedrock Action and Bedrock Streaming Action to directly invoke foundational models using the Converse and Converse Stream APIs.
This code snippet shows exactly how you instantiate a Bedrock streaming action with region configs and AWS guardrails within a Burr application builder. When you wire up a streaming model this way, Burr handles the complex state chunking entirely behind the scenes. Because it's a streaming action, intermediate tokens stream back to the user smoothly, and they're only written to your durable persistence database once the final cohesive result is fully assembled. Okay, on to interfaces, schemas, and scale. We're talking Streamlit, Pydantic, and Ray, because an AI agent is really nothing without UI prototypes, typed contracts, and distributed compute.
Streamlit is fantastic here. It provides incredibly quick interactive prototypes around a Burr app, which is absolutely perfect for rapid prototyping and visual debugging. Burr includes native utility functions that instantly render an explorer, a state machine tracker, your action nodes, and results. It is exactly what you need to rapidly test agent flows before you commit to writing a full front end.
And Pydantic integration is absolutely critical. It guarantees typed, structured state, giving you much safer contracts against unpredictable model outputs. Instead of letting your application state exist as some messy, unstructured dictionary, you apply a Pydantic model using the with typing method in the Burr application builder. So if an LLM hallucinates a malformed JSON payload, and we all know it will eventually, Pydantic catches it instantly, enforcing that rigid structured state and preventing bad data from corrupting your downstream actions.
Now what about scale? Burr does integrate with Ray for massive parallel execution via the Ray executor, which maps parallel sub-applications or actions across states. But we must pragmatically note this status is currently categorized as advanced and incubating. So if you need to map thousands of parallel sub-applications across a massive compute cluster, Ray is your bridge, but it should not be assumed to have turnkey durable persistence just yet. Approach it with proper testing.
Finally, let's talk about the visible state machine and managing the graph. We're going to pull all these modular building blocks together into our final architectural vision.
The overarching takeaway for you is that Burr does not make your tools disappear into hidden abstractions. It gives them a highly visible, inspectable place right on the graph. Integrations serve as nodes, helpers, or enclosed subgraphs. And while they do their specific job, Burr rigidly manages the tracking, the persistence, and the exact resumption boundaries. Now, a quick note on developer pragmatism. Because this ecosystem is actively evolving under the Apache Incubator, you need to always verify current documentation for supported features. Pin your package versions in your production pipelines for sure, and rigorously test serialization and resume behavior for each new tool before pushing to production. So we'll leave you with this question. If your AI framework hides your tools in a black box, how will you debug the invisible when the state machine breaks? By enforcing an explicit state machine, Burr ensures you can always see, trace, and resume your application's exact thought process.
Okay, let's dive into this. Welcome back to The Explainer. Today we're unpacking a massive headache for developers: testing, replay, generated test cases, and evaluation data for stateful AI systems, specifically looking at how the Apache Burr framework handles it all.
We've got a lot of ground to cover. We'll start with the AI testing challenge, then move into replay and forking execution. From there, we'll look at generating deterministic test scaffolding, asserting mechanics over strings, the tracking to test handoff, and finally, wrap up with the practical evaluation cycle. So, part 1, the AI testing challenge, or really just the reality of testing stateful AI. Look, if you've ever tried to test a stateful AI application in production, you absolutely know the pain. You might be wondering, why does testing stateful AI feel literally impossible sometimes?
Well, traditional software testing methods just completely break down the second large language models enter the chat. You write a test asserting a specific output, and literally the next day, the model gives you a slightly different synonym, and boom, your entire test suite is a sea of red.
And there are a few main culprits here. LLM outputs are by nature non-deterministic. They vary wildly. You've got unpredictable, endless workflow loops, you get compounding errors from past conversational turns, and honestly, the worst one, finding a bug deeply buried inside a tool result from like 3 turns ago. It's a nightmare. But this is exactly where Apache Burr steps in. By explicitly modeling your AI as a state machine, Burr makes every single execution step, state snapshot, action result, and transition fully observable, and, most importantly, reusable for your tests.
Which brings us to part 2, replay and forking execution. Think of this as time travel debugging.
Now, what's really interesting about this timeline is how it visualizes fixing broken AI workflows from first principles. Imagine a tracked run where a routing error pops up at sequence 4. Because Burr persists the exact state at every single step, you can inspect this run, pinpoint exactly where things went wrong, and reproduce it. You don't have to start all the way back at sequence 1 and just cross your fingers that the LLM behaves the same way to recreate the bug.
And that leads right into the concept of forking. Instead of rerunning the whole pipeline, you literally just rewind the state machine. You restart exactly from sequence 3. You fork from that exact historical state, inject a modified action, or maybe tweak your model configuration, and then replay the transition. You're debugging from the exact millisecond things went sideways. It's a total game changer.
Moving on to part 3, generating deterministic test scaffolding. This is all about deterministic tests.
So how do we actually turn these raw telemetry traces into real deterministic test code? Well, here's the concrete CLI workflow. Step 1, you track the execution in Burr. Step 2, you run the Burr test case create command right in your CLI. That's your entry point. This tool grabs the tracked state inputs and outputs surrounding a specific action, and step 3, it spits out realistic fixtures and deterministic PyTest-style scaffolding.
Looking at the generated test here, you can see how it reconstructs the exact state right before an action. Since determinism is the whole point, you mock or stub those external LLM calls. The test then runs the action and asserts the expected state shape, the routing decision, or the data transformation. The best part? You get to run your test with determinism without hitting those expensive, unpredictable AI APIs every single time your CI/CD pipeline runs. Huge relief, right?
All right, part 4, asserting mechanics over strings. This is the secret to resilient testing. So the crucial point here is understanding how to write resilient generated tests for apps built on non-deterministic models. On the left side, we've got brittle testing, asserting exact model strings. If you say assert output equals hello, your test breaks the second the model decides to say hi. It's super fragile. On the right side, though, we have resilience. You need to assert state transitions, routing, and schema. You really only want to use exact string assertions when the action is completely deterministic, or if you've deliberately frozen the model output.
Let's actually look at what mechanical assertions look like in practice. For instance, you assert that the intent must be one of a few known values. Or you assert that your chat history grows by exactly 2 messages per complete turn. You verify that a safety flag like approved is true before any send action happens. If a retrieval fails, you check that it writes a retrieval error and correctly routes to a fallback. You check that a tool action stores a structured observation for the next step, and that a streaming action only commits its final state when it's totally done. Basically, you are testing the mechanics of the state machine, not the poetry of the LLM.
Let's look at part 5, the tracking to test handoff, curating data.
We need to talk about how engineering teams curate this data to cleanly separate the stages of the software development lifecycle. Understanding this distinction is absolutely crucial. Tracking captures the raw evidence of what your application actually did out in the wild. But curation, that's where human engineers step in and decide what actually matters. From there, generated tests and evaluation datasets take that curated evidence and turn it into repeatable, durable engineering assets.
So in the Burr UI, this curation process means engineers are actively inspecting runs. They're filtering for failures, marking the golden paths, and labeling whether routing, retrieval, or safety gates behaved the way they were supposed to. Those curated examples then become your debugging packets, your PyTest fixtures, or your evaluation rows. You take all those findings and feed them straight back into your prompt edits, action refactors, and schema updates.
Finally, part 6, the practical evaluation cycle,
getting into continuous AI ops.
Zooming out to the enterprise level for a second, let's see how this fits into continuous AI operations. Here is your practical evaluation cycle. First, you collect real and synthetic runs. You redact any sensitive data, and you annotate for success or failure. Then you generate those deterministic tests for the state machine mechanics we just talked about. Now, crucially, you run entirely separate model quality evaluations for the probabilistic outputs. You compare results across Burr or model upgrades, and you only promote to production when both, and I mean both, the state machine tests and the evaluation metrics pass.
And this brilliantly illustrates the ideal operational engineering loop. You observe a bug in the Burr UI. You curate the relevant trace. You generate a test right from that state snapshot. You fix the action or transition. And finally, you replay the scenario, keeping that test forever as a guardrail in your suite.
Connecting these micro-level developer tools to macro-level operations is exactly what ensures a resilient production system. Tracked real-world runs, seed your regression suites, and your replay data. This continuously updates your evaluation set, ensuring that the exact same failure mode is measured accurately over time, even as your application evolves. It's like a self-healing loop.
So, we'll wrap up this explainer with a question for you to chew on. Will you leave your stateful AI behavior to chance, just hoping the LLM gets it right every time? Or will you use tracked evidence to build a deterministic, repeatable engineering asset? The tools to stop guessing and start engineering are right in front of us. Think about it.
If you've been working with generative AI, you know that making the jump from a local Jupyter Notebook script to a scalable enterprise-grade application is a massive leap. In this explainer, we're moving past local scripting directly into hard production concepts to deploy Apache Burr securely and reliably. We're going to look at exactly how to hook this state machine framework into modern web servers, persist its memory, and harden it inside containers.
Here's our roadmap for the architecture. We're covering stateless APIs and durable state, deploying the tracking UI and storage, handling real-time streaming responses, state sizing and storage, container isolation and security, and finally, we'll wrap up with the central in-process limitation.
Let's kick things off with Section 1, Stateless APIs and Durable State.
So to scale effectively, web servers like FastAPI are stateless by design, right? They handle a request, return a response, and completely forget who you are. But AI agents are inherently stateful. They absolutely have to remember the conversation. Burr bridges this gap by acting as a highly deterministic state machine. It uses specific session identifiers, like an application ID for the chat thread and a partition key for the user ID, to seamlessly connect those isolated HTTP requests into one continuous agentic loop.
Here's how that complete request lifecycle actually maps out. First, your stateless endpoint receives a request with those tenant and app IDs. Second, using a function called initializeFrom, it pulls or hydrates the exact historical state from your database, bringing that saved memory back into active use. Third, the Burr application runs your agent logic until it hits a halting condition. And finally, the updated state is safely persisted back to the database before it returns the HTTP response.
If you check out the code here, you can see how wrapping your Burr application builder inside a standard FastAPI route handler makes Burr act as an embedded engine. You just pass in your Postgres persister, set the parameter resume at next action equals true, and Burr entirely delegates all that storage complexity to the database layer. Your web server stays totally stateless and horizontally scalable.
Now, to pull off that continuity across multiple stateless containers, you've got to equip your application builder with one of these robust persister integrations. For local prototyping, SQLite works great. But for high concurrency production environments, Burr natively supports asynchronous Postgres via Async PG, Redis for sub-millisecond in-memory routing, and MongoDB for those highly unstructured, nested LLM outputs.
Moving right along to Section 2, deploying the tracking UI and storage.
Burr gives you incredible visibility, but how you deploy it definitely changes as you scale up. For local experimentation in a Jupyter or Colab notebook, you can just use the magic command %burrui. But for internal deployments, you can actually use mount_Burr UI to seamlessly embed the Burr UI right onto a FastAPI routing path. This gives you controlled debugging without having to spin up a completely separate server process.
If you're using Docker Compose, the shared volume pattern is literally your best friend. This connects isolated API and UI containers through a private network. Your API container writes local tracking data to a mounted Burr data directory, and then the separate UI container concurrently reads from that same volume to visualize your execution traces in real time. It's clean, it's isolated, and highly effective for single machine deployments.
However, here is the production reality check. The shared volume trick is fantastic, but across multiple virtual machines in a true cloud cluster, local volumes are ephemeral. You must migrate your tracking data to object storage, like AWS S3. Burr supports this with its S3 tracking server, but migrating away from local volumes introduces significant requirements for explicit security and data retention design.
All right, Section 3, Real-Time Streaming Responses. To solve the time-to-first token problem for chat interfaces, your endpoint can format Burr's output into server-sent events. Because LLMs return data over time rather than all at once, what we call an asynchronous generator, SSE acts as a streaming response pattern where FastAPI wraps those intermediate text chunks into standardized payloads. This drastically lowers perceived latency, giving users that familiar, snappy ChatGPT-like typewriter effect.
But designing these streaming actions requires strict adherence to a specific protocol. Intermediate chunks must yield the chunk data alongside a state value of none. By explicitly returning none for the state during those intermediate yields, you are telling the system to delay the database update until the stream is fully exhausted and the final, combined response is actually ready. Which brings up a very practical question for any software engineer. What happens if a streaming connection drops mid-generation? The user closes their laptop or the network flakes out. Doesn't that corrupt the database?
It's a super common production failure. But Burr's design actually protects your infrastructure automatically here. Because persistence waits for that final yield we just talked about, lifecycle hooks and database writes are intentionally deferred. Your backend database remains perfectly clean even if the client disconnects unexpectedly. No partial, corrupted states left lingering in your tables.
Next up, Section 4, State Sizing and Storage.
In Burr, the state dictionary is intentionally immutable and checkpointed at every single step. This means every serialized field essentially becomes infrastructure cost and potential privacy surface area. So you need to draw a hard line between what goes inside Burr's state and what stays outside. Keep raw large documents and massive dense vector embeddings outside of Burr. Only persist references, IDs, and summarized context inside the actual Burr state.
To manage this, you really want to enforce strict sizing rules. Keep your state schema compact, optionally using pedantic models to enforce structure, summarize old conversational context rather than appending to it endlessly, prune long execution histories. And if you're using S3 for tracking, enforce strict retention policies. These practices ensure your tracking UI remains lightning fast and your database doesn't just bloat exponentially.
Which brings us to Section 5, Container Isolation and Security.
The built-in local UI is an absolute superpower for debugging and building demos. However, true production monitoring demands a lot more. You need to integrate OpenTelemetry APM to link Burr steps with external services like Datadog. You need external centralized logs, deployment health checks, and role-based redaction to ensure sensitive user data isn't exposed in your telemetry streams.
You really need to isolate your architecture. Separate your UI, API, database, and proxy into distinct deployment components. Keep your databases and tracking stores locked down inside private networking subnets. Never hard-code keys. Use environment variables and secret managers. And critically, use versioned container images that explicitly pin your Apache Burr dependency to ensure reproducible builds.
And here is a massive security warning for sure. Do not expose your S3-backed tracking endpoints to the public internet. The source materials explicitly note that native authentication and access control lists for the tracking server are still incubating as future work. You must actively build a security proxy layer, like Nginx with authentication, in front of the telemetry server to protect your enterprise data.
Finally, Section 6, the central in-process limitation. Let's look at this quote. Burr is an in-process state machine and observability core inside your production system, not the entire orchestration platform. This is absolutely the key takeaway. Burr is not a massive distributed orchestrator doing everything for you. You are still responsible for designing the outer network queues, handling retries, planning disaster recovery, and configuring load balancers. But by making Burr the explicit, perfectly observable brain inside that robust external body, you gain total control over your AI agents. So the ultimate question is, now that you have this powerful, inspectable brain, what kind of production body are you going to build for it?
Let's dive right into the operational guardrails you absolutely need when safely deploying Apache Burr. When you're orchestrating AI systems, Burr gives us this incredible power through explicit state machines. But, with that power comes a necessary shift in mindset. We've got to move from just blindly trusting a framework's tracking capabilities to rigorously governing exactly what it tracks, what it stores, and what it executes in our production environments.
Because here's the first principle of defensive production with Burr. Its powerful observability is the exact reason we have to aggressively govern its data. Think about it. Whether you're just using the local tracker, writing to that hidden .burr directory, or you've deployed the full-blown S3 tracking server, the rule is exactly the same. If Burr tracks it, Burr stores it. Every single prompt, every intermediate tool result, every scrap of user text, it all becomes persistent telemetry. So our production governance simply has to match that level of data sensitivity.
To get there, we'll systematically deconstruct these production risks, looking at data privacy and secrets, performance limits, execution reliability, API stability, and finally, some practical production checklists.
Starting off with data privacy and secrets, and how we govern the state machine.
The absolute most crucial point here is identifying what does not belong in Burr's state dictionary. Period. Things like model provider tokens, database credentials, API keys, or unencrypted PII, those should never, ever be stored casually in persistent state, because if you put them there, they're going to show up in your telemetry UI and your database logs for anyone to see. Instead, these secrets belong in environment variables, secret managers, or as request-scoped runtime inputs that totally bypass the persistent state. So what goes in safe state? Things like S3 URIs or sanitized context.
Since Burr locally tracks all those prompts and intermediate reasoning steps, your production teams must actively curate this data flow. It's like being a bouncer for your own database. When designing your actions, intentionally map out how data is ingested and transformed. You have to make sure your logic redacts or encrypts sensitive fields before returning that updated state object to the tracker. Oh, and a quick heads up, if you're using the S3 tracking server, authentication is shared at the bucket level, making your architectural security absolutely paramount.
Moving right along to Section 2, Performance and Payload Limits, and keeping that state compact.
Look, shoving massive binaries, giant PDFs, or full multi-dimensional vector embeddings directly into your Burr state dictionary, that is a recipe for a production disaster. I'm talking severe slowdowns in serialization, database costs that will literally terrify your finance team, a totally cluttered Burr UI, and making the replay of historical states a complete nightmare. It's just bloated.
So, how do we maintain performance hygiene? You've got to rely on compact fields and external storage references. Have a heavy document, keep it in AWS S3, and just store the string URI in Burr's state. You also need to enforce bounded histories. Please do not let an infinite chatbot loop grow an array forever. And it's really important to note that the documented roadmap actually mentions Burr's current immutable state uses a somewhat inefficient copy mechanism, though functional optimizations are on the way. But for now, keep your state lean and your action granularity very deliberate.
Next up, execution reliability and retries, specifically focusing on handling side effects. We need to talk about idempotency. It's a big word, but it's absolutely crucial here. Think about an agent action that charges a customer's credit card or updates an external CRM or sends out a critical email. Now imagine your network hiccups, Burr retries that action, or a dev replays a state to debug something. You have to design those retries so those external side effects are never, ever duplicated. Nobody wants to be charged twice.
Right now, richer exception management flows and native retry handling are still incubating on the Burr roadmap. That means you cannot just assume the framework is going to magically solve every failure mode for you. You have to build defensive application-level safeguards today. Take a look at how we can do this. Using explicit state flags, like checking if an email_sent status is already true, acts as a circuit breaker. That simple check prevents a resumed workflow from spamming a user or slamming an external API twice.
And this builds perfectly into human-in-the-loop workflows. For those truly irreversible actions, just put them behind human approval. Burr actually natively supports this. By using explicit halt conditions, you can pause the state machine, which lets the persister save the exact context. Then, after a human reviews the draft in a UI, the backend rehydrates the state and seamlessly resumes execution. It's a brilliant way to guarantee safe external operations.
All right, Section 4, API Stability and Upgrades, or How to Navigate the Incubator.
The source materials are very transparent about this.
Burr is currently an incubating project at the Apache Software Foundation. As of June 22, 2026, it's a podling, with version 0.42.0 incubating being the latest official release. So what does that mean for you? Well, it benefits from Apache's rigorous governance and vulnerability handling, which is great, but it hasn't fully graduated yet. The documentation is still evolving, and some features are explicitly marked as experimental.
Because of that, to ensure stability in your deployments, you must treat only the documented public API in the reference docs as your reliable contract. Anything undeclared or internal, treat it as highly unstable. You absolutely need to pin your specific Apache Burr package versions in your requirements files. Read those release notes thoroughly before you upgrade, and please, always maintain a small compatibility smoke test graph in your CI/CD pipeline. That's going to catch any serialization or transition breaks during your updates.
Finally, let's bring it all together with our production guardrails checklists for adoption and hardening. Before you even think about adopting Burr for production workflow, run through this evaluation checklist. First, confirm you're on the correct release line. Verify the current docs. Look closely at whether your exact ecosystem integrations, like Haystack or Ray, are mature or marked experimental. You'll want to prototype your persistence and resume paths using your actual application state, and thoroughly test the serialization of your Pydantic models or custom Python objects. And of course, figure out your exact security and access control needs right up front. Once you've adopted it, you need to enforce this practical guardrail checklist continuously. Validate your required state keys and schemas at every single step. Physically isolate irreversible actions from your standard reasoning loops. Centralize your external side effects so you can actually monitor them. Redact sensitive fields before they ever hit the tracker. Define strict retry and timeout policies per action. Monitor those error rates in production. And, this is a big one, never push a Burr version upgrade without rehearsing your database rollback plan first. At the end of the day, Apache Burr dramatically improves your visibility and control over complex AI behaviors. It totally removes the black box of LLM orchestration. But remember, the framework isn't going to automatically secure your data or design safe side effects for you. Your engineering team completely owns secure deployment, retry design, performance hygiene, and operational hardening. So leaving you with this to chew on. Are your AI agents currently operating with this level of disciplined production hygiene, or are you just blindly trusting the framework to catch you when you fall?
Okay, let's dive right into this. The AI orchestration space is moving insanely fast right now. You know how it is, moving from simple single-turn prompts to these massive, complex, multi-turn agentic workflows. That underlying architecture, it's literally the difference between a system that scales reliably and one that completely collapses under its own unpredictable logic. In this explainer, we're going to objectively evaluate Apache Burr, which is currently an incubating framework, and see exactly how it stacks up against the heavyweights in the ecosystem like LangGraph, Temporal, and popular multi-agent frameworks like CrewAI. The goal here isn't to declare some ultimate winner in a vendor battle. We just want to give you a clear, pragmatic decision matrix.
So here's our agenda. First, dimensions of AI orchestration. Then, Burr versus LangGraph, Burr versus Temporal, and Burr versus CrewAI. After that, we'll look at maturity and security posture, and finally, wrap up with final fit guidance.
Section 1, Dimensions of AI Orchestration, establishing the baseline. To evaluate these tools properly, we really have to start from first principles.
So I want to pose this question directly to you. What actually defines predictable AI orchestration? Early on, a lot of agentic frameworks leaned heavily into these black box magic loops, which is great for rapid prototyping, right? Because they hide all the complex control flow. But in an enterprise environment, yeah, that magic fails hard. It's kind of like giving a really enthusiastic but totally unpredictable intern the keys to your production database. When an LLM agent gets stuck in an infinite loop or hallucinates some destructive tool call, you need to know exactly why it happened. You need to know the exact state right before it failed and how to fix it without rerunning a massive, expensive pipeline. Real predictability means eliminating hidden control flows.
And that brings us right to Apache Burr's core architectural identity. Burr tackles this exact problem by forcing developers to express their applications as explicit, action-driven state machines. It operates entirely in process and is completely dependency-free at its core, making it a very Python-first tool. Furthermore, it is intensely agnostic. It honestly doesn't care if you use OpenAI, Anthropic, or run local models. It doesn't care what prompt engineering library you use. And what's incredibly unique is that it pairs this total neutrality with a built-in local-first tracking user interface.
To see what I mean by explicit, take the @action decorator in Burr, for example. The framework is essentially forcing you, the developer, to expose your data dependencies right up front.
This isn't your typical implicit agent code where variables are just floating around in some shared context. If an action doesn't declare that it needs a specific piece of state, it cannot read it. If it doesn't declare it will write to it, it cannot modify it. This is a mathematically strict contract, and it absolutely kills those hidden side effects that always seem to plague complex LLM pipelines.
Section 2. Burr versus LangGraph, Ecosystem Coupling versus Neutrality. With our baseline set, let's evaluate ecosystem dependence.
Now, both of these frameworks are fantastic at modeling graph-like agent workflows, cycles, streaming, the whole shebang. But their underlying philosophies on ecosystem integration are totally different. LangGraph is deeply and highly optimally woven into the broader LangChain ecosystem. If your team is already heavily invested in LangChain's abstractions, LangGraph is going to feel supernatural. Burr, on the other hand, takes a pure bring-your-own-stock approach. It's completely unopinionated about the tools you put inside your actions. So for teams that want pure Python building blocks and wish to avoid getting tied to LangChain's specific layers, Burr's neutrality is a massive draw.
Now, what's really interesting here is the approach to observability. It's a major differentiator. LangGraph leans heavily on Langsmith, which is a commercial SaaS platform, for its deep tracing and evaluations. It's incredibly powerful, for sure, but it is an external service. Burr goes a different route. It actually ships with a built-in, open-source local tracking UI. The second you run your application, Burr logs telemetry directly to your local file system, and you can visualize it instantly. For teams working in highly compliant, air-gapped on-prem environments, having a self-hostable UI straight out of the box is a huge architectural advantage.
Section 3. Burr versus temporal, in-process control versus distributed durability. Let's shift our focus over to workflow orchestration.
So temporal is an absolute powerhouse for asynchronous event-based orchestration. We're talking distributed, durable workflow execution with massive platform-level guarantees across multiple languages. If you're building generic, large-scale, long-running microservices, temporal is the gold standard. Burr, however, is much lighter. It's Python-centric, runs in process, and is laser-focused on stateful AI and developer-controlled graph logic. Burr isn't trying to be a heavy-duty multi-language infrastructure platform. It's trying to be a precise, perfectly inspectable state machine for decision workflows.
To make this concrete, let's look at persistence. By calling initialize from, passing in an SQLite persister, and setting resume at next action to true, Burr can persist its immutable state to a database and cleanly resume an interrupted workflow right where it left off, which is absolutely brilliant for human-in-a-loop AI tasks where an agent might wait days for user feedback. But, and this is a key distinction, this relies on your database and your application logic. Burr itself isn't automatically a full distributed durable execution platform the way Temporal's cluster architecture is.
Section 4. Burr versus Crew AI and LangChain agents. Explicit control versus role-play abstractions. Let's see how Burr compares to the popular multi-agent frameworks.
Frameworks like Crew AI are phenomenal for rapid prototyping. They use these role-based abstractions. You basically tell the system, hey, you are a researcher, you are a writer, go collaborate. It leans heavily on black box autonomy and shared LLM context to figure out the steps. It's super fast to set up, but you trade away control. Burr operates on the exact opposite philosophy. Its strength is absolutely not prompt-based role-play magic. Its strength is rigid, mathematically sound state machine modeling. You don't just hand it a researcher hat and cross your fingers. You explicitly design every single action, state mutation, and transition yourself.
The routing logic here is the critical piece. In role-based systems, routing is usually implicit. The LLM is internally deciding when a task is done based on the prompt. But in Burr, transition logic is explicit Python code. You define the edges between your nodes using functions like when_status=active, or maybe by evaluating a string expression like expressVasions and n greater than 3. Because you have to use explicit Python expressions for your graph edges, Burr completely eliminates hidden control flows. You know the exact mathematical condition required for your application to move from node A to node B.
Section 5. Maturity and Security Posture, Navigating the Apache Incubator. Let's be real, architectural purity doesn't matter much if the software isn't ready for production.
Let's move to the timeline and see how this builds. Burr has evolved incredibly fast. The earliest public package dropped in February 2024, followed by a formal launch from Dagworks. But the major governance milestone hit in May 2025, when the project entered the Apache Incubator. This means it is now undergoing rigorous open-source governance training overseen by the Apache Software Foundation, which is great for protecting it against commercial vendor lock-in. Fast forward to May 2026, and we see the official Apache release of version 0.42-incubating.
However, it is absolutely vital to remember that Burr is currently an incubating project. It is not yet a graduated, top-level Apache project. The roadmap still has planned work for things like exception handling and more efficient state management. Practically speaking, if you adopt an incubating project for mission-critical enterprise systems, you have to take responsibility for your own release hygiene. That means strict version pinning, rigorous upgrade testing across your Python environments, and thorough internal security reviews. Larger, older ecosystems simply have a broader public adopter base today, and you have to factor that in.
On the security front, there are some specific constraints you really need to understand to build a safe operational envelope. First, Burr's telemetry is highly detailed. It captures exact state inputs and outputs. This means your prompts, the LLM responses, and potentially sensitive user data are all being persisted to your local disk or database. Second, if you use the S3-backed tracking server for production, the docs currently list authentication and access control lists as future work. Securing that bucket is on you. But, on a positive governance note, the 0.42.0 release actually stripped out phone home telemetry completely to align with strict Apache Foundation privacy policies.
Section 6. Final Fit Guidance. The Pragmatic Decision Matrix. Let's pull all these threads together into a synthesis you can actually use.
This matrix really sums up the whole explainer. You should absolutely choose Burr when you prioritize inspectable, pure Python control flow. If you want a self-hostable UI for air-gapped observability, easily pluggable persistence and replay, and you prefer explicit mathematical transitions over LLM-driven magic, Burr is a phenomenal fit. On the flip side, you should look elsewhere if your primary requirement is multi-language, distributed workflow durability, go to Temporal for that. If you want mature, access-controlled observability as a service tightly coupled to your orchestration, LangGraph is your tool. And if you just want turnkey, role-based agent abstractions with minimal setup, look at Crew AI. At the end of the day, building truly reliable AI applications means confronting the chaotic nature of language models with the rigid discipline of classical software engineering. So the real question you have to ask yourself and your entire engineering organization is this. Are you ready to finally trade the allure of black box magic for deterministic, inspectable Python control flow?
Transitioning your Apache Burr skills from initial blueprints directly to a production-grade architecture, it requires a mindset shift. If you've been working with generative AI, you know the struggle, right? Scaling up from a simple prompt response script to a complex multi-turn agent usually turns into a massive tangled mess. Well, in this explainer, we're going to fix that mess.
Here is the roadmap. We are looking at core AI design patterns, non-LLM state machine patterns, code and payload pitfalls, release and operational risks, and finally, refactoring for production.
Section 1. Core AI Design Patterns. Let's dive right into those foundational blueprints and see exactly how specific logic translates into a visual graph shape.
First up is the classic router pattern. It goes like this. You classify the input, explicitly write a clear routing state field to your dictionary, and then transition to the appropriate action. By explicitly writing out that field, conditional transitions, using functions like when or express, know exactly where to send the execution next. There's no hidden control flow here. It is 100% explicitly graphed.
Next, we've got the human approval pattern. This one is brilliant because it leverages Burr's explicit halt conditions to safely pause execution. So, you define a state machine that generates a draft, but you use halt before on the approval node. Boom, the state persists to your database, totally releasing the server thread. Later on, human feedback is injected using the step function, and the graph safely resumes and revises.
Other critical patterns basically just rely on passing explicit keys through that state dictionary. Take the tool execution pattern. The graph loops to choose a tool, executes the action, stores the observation in state, and responds. Or the RAG pattern, you retrieve context, generate an answer, and track a specific citation state key. And for a multi-agent pattern, you just model specialized agents as individual actions or subgraphs handing off explicit state objects.
Section 2. Non-LLM state machine patterns. Remember, Burr is completely framework agnostic. Its real power totally shines when you drop the AI and use it for raw deterministic logic.
Using the exact same primitives, you can run event simulations or hyperparameter tuning. No LLM required. A simulation pattern just advances from event to event, perfectly preserving the scenario state at every single tick.
Meanwhile, a hyperparameter tuning graph writes a trial configuration, runs an eval, records a score to the state, and transitions to the next trial or the final winner.
Whether you're building a stateful adventure game routing between scenes with inventory changes and win/loss conditions, or you're running a what-if analysis, it is all just state and transitions. By using Burr's fork from sequence ID method, you can fork from a previously persisted sequence point, change an alternative decision, and compare the outcomes.
I want you to really memorize this core mantra for thinking in Burr. Important decisions become named actions and transitions. Important memory becomes explicit state. And important pauses become explicit halt conditions. Map your business logic to those three rules, and your architecture is going to be incredibly solid.
Section 3. Code and Payload Pitfalls. Now we need to look at the traps developers fall into when they carry over bad habits from standard procedural Python or quick tutorials.
Let's squash these common coding mistakes right now. First, do not hide all your logic inside one giant action. And whatever you do, do not mutate state in place. Always use .update or .append. Mutating in place completely ruins your ability to replay or debug historical traces. Also, never rely on ambiguous state fields for routing. And never forget a default fallback transition, or your app might just deadlock. Finally, don't treat tracking as durable persistence. And please don't write brittle tests that assert exact LLM wording. Use Burr's testing tools to mock outputs and verify deterministic transitions instead.
Payload size and performance is another massive trap. Seriously, do not shove a giant PDF, a live database handle, raw tensor embeddings, a full API response object, or an entire unbounded conversation history into Burr's state dictionary just because it feels convenient. Keep heavy artifacts in the appropriate external store. You need to refactor your state to only hold small, meaningful references, like a document_ID, a vector store key, an object URI, compact summaries, and structured routing fields. Keeping the state compact makes visualization, persistence, replay, and testing drastically easier.
And here is a golden rule for concurrency. Do not use async actions with blocking dependencies and expect it to magically work. An async Burr application has got to be async all the way down. If you declare an action as async but then drop a synchronous, blocking database call inside it, you're going to block the entire event loop. Keep it fully concurrent with proper async libraries.
Section 4. Release and Operational Risks. Let's talk about compliance and security API mistakes, which are super easy to miss since Burr is incubating within the Apache Software Foundation. First off, ensure you're using the new Apache Burr package name. Don't blindly copy over old pip install Burr commands into a new project without checking. Also, when compliance actually matters, you must distinguish between official ASF source releases and standard convenience artifacts like wheels. And never, ever upgrade an incubating framework in production without reading the release notes, checking for public API usage changes, and running replay or resume tests. Operationally, you have to be extremely careful. Because Burr persists everything in state for telemetry, any secret or regulated data you carelessly leave in there literally becomes a logged vulnerability. Apply strict access controls to your tracking data. Also, don't rely on remote S3 tracking options as a fully secure telemetry product right now. Authentication and ACL support are literally listed as future work in the docs. Oh, and do not confuse Burr's in-process resume model with a fully managed distributed workflow engine. They are entirely different beasts.
Section 5. Refactoring for production. Finally, let's synthesize all these rules by tearing down some messy procedural loops.
Think about a typical agent loop. A massive while-true loop stuffed with if statements is an absolute nightmare to debug. But by exploding that giant action into distinct nodes, like classify intent, retrieve context, execute tool, draft answer, human review, and final response, your graph suddenly becomes the actual living documentation for your business logic.
And this kind of explicit design applies perfectly to non-LLM workflows too. Break a massive, untrackable scenario loop pipeline into explicit nodes. Load scenario, apply event, score outcome, fork alternative, and summarize results. By doing this, your operational checklists literally become part of your engineering design, and that compact state heavily improves both your performance and your reviewability.
So, take a hard look at your current generative AI code base. Does your architecture serve as living documentation, or are your critical decisions still hiding in the dark of some massive while loop? Stop letting hidden control flow dictate your technical debt. Start leveraging Burr's explicit state and transitions to bring those decisions into the light, and your production pipelines will absolutely thank you.
Okay, let's dive right into it. This is the ultimate synthesis of our 24-part explainer journey, culminating in a fully production-ready Apache Burr application blueprint. Throughout this series, we've unpacked the nuts and bolts of state machines, LLM orchestration, and telemetry. But today we bring it all together into one cohesive architecture. We're going to build a fictional but entirely grounded enterprise support assistant. And to be clear, this isn't just some toy loop. This is a robust blueprint that takes a customer question, routes the intent, pulls context, fires off tools, streams the output, physically pauses for a human review, and flawlessly persists state across stateless web requests.
So here's our roadmap for today. We'll cover the production AI assistant, take a parallel lane into data science, look at Apache governance and releases, tackle security and reliability hardening, and finish up with the final adoption rubric.
Let's kick things off with part 1. The Production AI Assistant.
Now imagine how we flow deterministically through this process. Our first action, receive input, simply writes the user message to state. Next up, classify intent, figures out what the user wants and writes both the intent and a calculated risk level. Based on that, retrieve context steps in and writes document references. And crucially here, we're talking about compact context summaries, right? Not massive heavyweight corpora. Then, maybe execute tool handles the heavy lifting, writing structured tool output or maybe an external result ID. From there, draft response kicks in, streaming the partial output back to the user and saving the full response to state once it's done. But here's the really cool part. If that initial risk level is flagged as high, our review gate decides that a human needs to look at it, and it literally pauses the execution. From there, a process feedback node can loop us back for a revision before we finally hit final response and wrap up the request.
Translating this into Python is surprisingly straightforward. You'll notice that every single action explicitly declares the exact state keys it reads and writes using the action decorator. Take a look at classify intent. It explicitly reads the user message and writes the intent and risk level. Why does this matter? Well, it completely eliminates hidden control flows. Burr mathematically ensures that no action tries to read a variable that hasn't been initialized or explicitly written by a previous node. It's totally bulletproof and dramatically reduces those terrifying runtime key errors you often see in long-running LLM pipelines.
Next, we take that core graph and wrap it in a production architecture. In an enterprise setup, you're going to place your Burr state machine inside a stateless FastAPI service, probably running in Docker containers. And because FastAPI itself is stateless, the continuity of our AI assistant relies entirely on an application ID and a partition key to survive across web requests. So a request comes in, the FastAPI endpoint queries an external Postgres or S3 persister, rehydrates the exact Burr state using that application ID, and just resumes the graph right where it left off. Meanwhile, the built-in tracking client is quietly buffering telemetry data to OpenTelemetry traces or a self-hosted Burr UI. So your web server stays nice and light, while Burr and your database handle all that massive memory complexity.
Moving on to part 2, let's look at a parallel lane, data science.
Now here is a crucial point you need to remember. Burr isn't just for LLMs. Because it's a generic, pure Python state machine, we can build a totally parallel blueprint lane. The exact same architecture we just used for a chatbot can power robust data science and simulation workflows. Instead of agentic loops and streaming tokens, your nodes might be things like load experiment, generate trial, run simulation, and score result. And because Burr persists the state sequence at every single transition, you unlock incredibly powerful operations like fork what if. You can literally branch a brand new application instance off the historical state of a completely different session. This opens the door for Monte Carlo-style branches, hyperparameter sweeps, and complex what-if comparisons, all using the exact same persistence, tracking, and replay concepts from our AI assistant.
Let's shift gears to part 3, Apache governance and releases.
As we scale this application into a real production environment, we hit the outer walls of our architecture, release hygiene and governance. Burr is currently an incubating project at the Apache Software Foundation, so your team needs to follow some specific practices. First off, make sure you install the Apache-Burr package. You really want to avoid any legacy assumptions tied to the older, simple Burr package name. Also, be sure to record its Apache incubating status in your internal architecture notes, just acknowledging that while it's highly stable, it is technically pre-version 1.0. In a production blueprint, you've got to pin your version strictly. And absolutely crucial here, if your enterprise has strict supply chain security rules, you should verify the official Apache source artifacts using project keys and SHA-512 signatures. Treat standard PyPy wheels purely as convenience artifacts, not the ultimate source of truth.
To manage this, you've got to build a mandatory upgrade pipeline right into your CI/CD process. You don't just run standard unit tests and promote a new version of Burr.
Instead, use the Burr Test Case CLI tool to actually replay representative historical tracked runs from your real production data. You need to explicitly test those resume and fork behaviors and validate your real serialization payloads. You want to be 100% sure your Pydantic models or custom objects still serialize perfectly to PostgreSQL or SQLite. Only after all that checks out do you promote the new version.
Okay, Part 4, Security and Reliability Hardening.
Let's talk about securing this infrastructure against enterprise vulnerabilities and performance bottlenecks. Interestingly, the very feature that makes Burr so powerful, its exhaustive state tracking, is also its biggest security consideration. You must actively redact sensitive state fields from your telemetry. If you're using an S3-backed tracking server, you need to proactively review it for access control gaps. Slap strict authentication and network controls on there, especially since some of these controls are noted as future work in the early incubating releases. On the reliability front, ensure all your tool calling side effect actions are idempotent. That just means if an accidentally runs twice because of a network hiccup, it won't corrupt your external systems. Enforce explicit retries for those flaky external LLM APIs, and always make sure your state snapshots store compact schemas like references or summaries rather than giant heavyweight document payloads. That's going to keep your database latency nice and low.
And finally, Part 5, the final adoption rubric. So, we have reached the ultimate decision point. Before you commit real engineering resources to this blueprint, how do you know if Burr is actually the right choice for your team? Well, Burr is a massive asset, a really strong fit when you explicitly want inspectable Python state machines. If you need transparent AI agent control flow with zero hidden magic, if you require human-in-the-loop workflows where the graph physically pauses for approval, or if you want self-hosted observability without shelling out for a pricey SaaS platform, Burr is absolutely exceptional. But keep in mind, it might be a weaker fit if your enterprise strictly demands a deeply mature, multi-language distributed workflow platform. If you need temporal-level platform guarantees across Java, Go, and Python right out of the box, or if you just need the largest possible public adopter ecosystem today, then you might want to look at other options.
All right, let's cement this crystallized core loop in your brain, because this is the real blueprint. We define immutable state, we mutate it via explicitly contracted actions, we route logic using conditional transitions, we wrap the whole thing in an application builder, we track the execution locally or remotely, we persist it to a database, we resume it seamlessly in a stateless web server, we verify our upgrades carefully, and we harden our security.
So, I'll leave you with this. Think about your current projects. Look at the chaotic, unpredictable AI workflows sitting on your desk right now. You know, the ones relying on fragile while loops and massive prompt chains hoping for the best. What unpredictable, complex workflow will you finally bring to order by wrapping it in the deterministic, auditable control of a state machine?